Thank you.
All right. Good morning. As the chair of the 2022 Transportation Consortium of South Central States, shortly named Tran-SET Summit on Durability of Transportation Materials, I am pleased to welcome everyone at today's summit. As you know that we have about 150 people that registered for this hybrid mode of the summit. Of this, about 30% people, they registered for face-to-face, and then the rest is virtual. And the virtual attendees are from 7 countries in the world that include, of course, the United States of America, Bangladesh, China, Finland, India, South Korea, and Saudi Arabia. And we have a representation from 13 states within the USA, and Arkansas, we take the most share here. So yeah, congratulations. Then it's random order. There is no other kind of like who has the most or less. Louisiana, Texas, Oklahoma, Iowa, Missouri, Massachusetts, New Mexico, Nevada, New York, Oregon, Washington, and Wisconsin. Thank you all for participating and for lending your expertise on this important topic. I'd like to acknowledge the financial support of U.S. Department of Transportation through Tran-SET for sponsoring this summit, as well as other research projects Federal Highway Administration Region 6 that includes Arkansas, Louisiana, Texas, Oklahoma, and New Mexico. My sincere appreciations are due to Tran-SET Director, Dr. Marwa Hassan from Louisiana State University for leading the efforts of the Tran-SET for last 7 years. And we hope she will continue to do so for many more years to come. I am very thankful to all the speakers making their time available for this summit. We can start such a short notice. I appreciate all the former and current advisory members of Tran-SET, in particular those who have represented Arkansas, that include Ms. Elisha Kingride, Mr. Chris Daly, and Mr. Mark Hadley, all from Arkansas Department of Transportation. I would also like to thank all Tran-SET project review member committee, especially those involved with Arkansas State, that it include Mr. Alan Matters, Mr. Can some of you please mute your microphone? Thank you. Mr. Craig Light from the city of Jonesboro, and Dr. Ruzbe Gafsi from South Dakota State University. My sincere appreciation is due to the summit organizing committee members and several individuals that include Tran-SET Program Director, Dr. Hina Dashmana, Ms. Kameshia Stinnett at A-State, and my graduate students, Abu Akid, Faris Tarhuni, Rupesh Mahat, Omar Pasha, and Samir Sadat, for all their help in providing the logistics support in organizing. Please do not mute me. Thank you. I have a few co-hosts I made, so one of them probably muted me. So that means that the others, they cannot hear me. Thank you. We have gathered an impressive lineup of speakers who addresses range of diversified group of researchers, industry experts, and policymakers. The topics will cover construction and implementation of solutions up to the problem related to geotechnical, bridge construction, and paving materials. We will also hear for some welcome remarks from a couple of Arkansas State dignitaries that include the Dean of College of Engineering and Computer Science, Dr. Abhijit Bhattacharya, and the Chancellor, Dr. Todd Shields. Thank you. I appreciate everyone again for making the time and stopping by or spending the whole day or whatever the time you could manage, and enjoy the summit. So some of the housekeeping items, like those who are here face to face, for the Wi-Fi connection, use IS reward, that is your Wi-Fi network, and password is 761803. And the schedule for today's summit is on page 5 of your booklet. And it has like on-site registration followed by breakfast, and then we'll have brief remarks from College of Engineering and Computer Science Dean, followed by technical presentation. And then right before lunch, we'll have Chancellor remarks. And then there are a couple of other technical sessions, and there will be a short break in between them. And we plan to adjourn around 4 o'clock. And presentations will be recorded. Actually, the entire meeting is being recorded. And in case we have to get out of this room for any kind of emergency situation, hang on there, we'll regroup and join, and we'll start according to the time. Whenever that presentation is, we'll restart from there. But we'll finish anyhow, we'll finish at 4 o'clock. And professional development hours, those who are attending here, there is a record sheet in your bag, that goodie bag that you have. There is one page Excel sheet that has been printed there. Record your time at the end. Whenever you leave, just return that to one of us. And those who are online, I emailed you. Please record your time and email it to me according to the direction given in the form. So now at this time, we are going to listen from our Dean of College of Engineering and Computer Science. He was eagerly waiting for this and wanted to give in-person speech, few minutes, but at this moment he is traveling. He is on a flight. His flight starts at 10 o'clock from Little Rock. All right. Before that, Mr. Broadway, do you want to say thank you? Yeah, thank you. Before that, I would like to welcome Mr. Shane Broadway with the ASU System Office, and I am going to let him introduce himself, so I do not want to, so I do not do any mistakes.
No, you're fine. You're fine. Good morning, everyone, and welcome. My name is Shane Broadway. I'm the Vice President for University Relations for the Arkansas State University System. And I am honored to be here to come by and support my friend and colleague from Arkansas State University. I know, and the Chancellor's going to be on in a little while. He's probably working out. I've made the comment, if you've not met our Chancellor, Todd Shields, that my Chancellor can outlive yours. He is in much better shape than any of us on the rest of the campus, outside maybe the football team. But right now we got so many injuries. He's probably the least injured person we got on campus. So, but it is a pleasure to work with such a distinguished group, Dr. Hossein and his students and the College of Engineering at Arkansas State University. I was remarking earlier, my father retired from the Arkansas Highway and Transportation Department at the time, RDOT now, and I still have several family members who work at RDOT, and so always holds a special place in my heart for my dad's time there and the people that he had the honor to work with. He's now deceased, but we still think a lot of the place, and I drive by it every day. I live in Bryant, even though I work for the ASU system. So people making roads and bridges and maintaining those have always been a part of my life. Listening to my dad drive down any interstate or any highway, I learned a lot about highways and transportation and bridges and all of those things. And so it's always been of great interest to me. And so now it's kind of life comes full circle that I spend every day working with people in engineering, educating the future engineers of those bridges and roads and construction. To be a part of that is kind of how life sometimes has a funny way of coming back around. And so I just want to thank all of you here and online for what you do for our university, on behalf of our university, but for our state, for the state that you represent. It is important to have these meetings and have a collective gathering of people. I always said when I served 14 years in the legislature, I'm not an expert on anything. The only thing I was an expert at was putting the right people who knew what we need to do in the room and figured it out. And that's what these meetings are about, is putting the smartest people together in a room, talking about problems, coming up with solutions, looking at data, looking at research, and how we can make everything better and safer for those who are traveling on our interstates or highways or bridges or whatever construction it might be. If we can make it better for everybody else where they don't even have to think about it when they get on the road, then your job has been successful. And so I appreciate all you do. I look forward to working with you. I've got to run and head back to the Capitol, but I appreciate Dr. Hossain and all his people for putting this together so quickly. I do want to thank our application has been resubmitted for another round. And so I do want to thank Senator Cotton and Senator Bozeman and Congressman Crawford. Senator Cotton's office took the lead. He contacted me about getting a letter of support from our congressional delegation. And so you folks from Arkansas need to know his office took the lead and got Senator Bozeman and Congressman Crawford in a short amount of time to sign on to a letter to support the continuation of this program. And so I want to thank them publicly as well. So you didn't come to listen to me, but I hope you have a great rest of the day, and I appreciate the opportunity to be with you.
Thank you very much, Mr. Broadway. All I can say, he is a very good friend of mine and ours. Thank you again for stopping by, Shane. All right, so let's move on to the Dean's message. Before that, I'll take a couple of minutes to introduce him. I put up his short bio. So Dr. Bhattacharya took his position as the inaugural Dean of the College of Engineering and Computer Science on July 1st of 2019 at Arkansas State University. Prior to moving to Arkansas State, he was at the University of Arkansas at Little Rock for almost 17 years in a variety of faculty and administrative roles. In his current role, his passion is for academic program development, expanding opportunities for high impact student experience, as well as research opportunities for students and faculty. A mechanical engineer by profession, he has made significant research contribution in the area of composite materials, thermomechanical characterization of smart materials, shape memory alloys, and piezoelectric materials and thin films. He got his PhD in mechanical and aerospace engineering from Rutgers University. He has been funded by NASA, NSF, EPSCoR, Department of Energy, Army Research of Office and Defense Advanced Research Program Agency, DARPA. He is an avid program evaluator and is a fellow of American Society of Mechanical Engineers. So let us now play the video message that he has given it us. I'm going to play this and give a pause to make sure that you can listen. This is one of the problematic areas, like always we have with Zoom. When you play video, the audience, the remote location cannot hear.
Greetings from the College of Engineering.
Okay. Someone already confirmed, but can someone speak? Can you hear it? The video. Did you see the video? At least hear it?
Yes.
Can another person confirm, please?
Yes, we can.
All right, great. Thank you.
Greetings from the College of Engineering and Computer Science, Arkansas State University. In my capacity as the Dean of the college, I consider it my privilege and a pleasure to offer remarks at the 2022 Transportation Consortium of South Central States Summit. I regret that this is a recorded message. I'm on travel right at this very moment. This summit is being attended by almost 150 participants from 7 countries. I congratulate the conference organizers, especially my colleague, Dr. Zahid Hussain, who has worked tirelessly to make this conference a success. Now, as many of you are aware, Tran-SET consists of 11 academic institutions in Arkansas, Louisiana, Texas, New Mexico, and Oklahoma. It has focused on solving transportation infrastructure problems through the development, evaluation, and implementation of cutting-edge technologies, novel materials, and innovative construction management processes in Region 6's University Transportation Center since 2016. Like other consortium members, Tran-SET funds have facilitated students' learning and professional development at A-State. Throughout the last 6 years, Tran-SET research has supported over 30 Arkansas State graduate and undergraduate students and engaged 10 faculty members in active research and professional development activities, such as the 2021 Tran-SET conference hosted by A-State last year. Tran-SET not only focused on innovation and implementation of research outcomes, but it also puts significant efforts into building future transportation workforces through activities such as scholarships, internships for undergraduate and graduate high school students, e-cyber mission competitions, and project-based STEM events in the region. These opportunities are especially important in the northeast corner of the state of Arkansas, where we are located. The College of Engineering and Computer Science is host to strong programs in civil engineering, electrical engineering, mechanical engineering, computer science, and engineering technology, as well as new programs in data science and data analytics, land surveying and geomatics, construction management, and engineering management systems. High-impact student experiences, including research, are a top priority in the college. Research is funded by a variety of agencies, including US DOT, RDOT, NSF, DOE, and NASA. Over the last 3 years, enrollment in the college has increased 29%, and research awards in the 4 months of this fiscal year, just 4 months, already has exceeded fiscal year 2020 awards by 73%. I'm encouraged to see a great lineup of speakers representing government agencies, industries, and academia at this event. My best wishes to you all for a very successful conference. Thank you, and wolves up.
I appreciate our Dean for delivering such an wonderful message. And now let's move on to the technical presentation session. This is session number 1. And the first speaker of this session is Mr. Paul Tinsley. He will be delivering a couple of presentation here from this room. Mr. Paul Tinsley graduated from Arkansas State University in 2001. Paul began his career at RDOT in 2002. He worked in the construction division for 9 years before transferring to the geotechnical section of the materials division in 2011. Paul led the geotechnical section until 2020, when he was promoted to assistant division head of materials and was named Materials Division Head 2022. So please help me welcome Mr. Paul Tinsley to deliver his presentation. All right, Mr. Tinsley.
Is this one? Yep. All right. Good morning, good morning. Lively bunch you've assembled here this morning, Doc. I hope y'all are sleepy because you had as much fun as I did last night. Halloween was awesome. We pulled the deep fryer out in the front yard, did homemade corn dogs and deep fried Oreos. And it turned into a neighborhood party, a few gallons of beverages later. And I'm pretty sure I'm the only person in my neighborhood that didn't call into work this morning. Now, I'm not saying you're lucky to have me, but I'm lucky to be here. A lot of friendly faces in the audience today. Those of you that know me know that behind this podium is not my comfort zone. It's about 7 tables back. So bear with me, and those of you that are joining from afar, just know that when they schedule the speakers, they started on Crayola level and calligraphy level. That'll come later on this afternoon. But I do like talking about landslides, so maybe I can tell you something that you didn't know. Prior to about 2015, the department's unwritten policy in regards to how we manage landslides went something like this. Roadway would drop and crack and start to move, and we'd overlay it. And it would drop and crack and move again, and we'd overlay it. And year after year, that's what we would do until we had however much it took to reach a tipping point. So what I found is once you overlay enough to put about 5 or 6 feet of asphalt on a roadway, you've added just enough weight and driving force and stop the water flow through material to cause a catastrophic failure. So what we did is just that. We would overlay. We really didn't have a proactive approach or even the ability with our funding to be proactive. So we would wait till we had a catastrophic event. And then the only tool that we had in our toolbox was a rock buttress. And rock buttress has its place. If you can't see it from space, it's usually not big enough. And they tend to get bigger and bigger as we build. So some of the downfalls to a rock buttress are, as soon as you get started on construction, you remove material, and your excavation adds to the instability, which leads to a high probability of closing a road if you've already got a lane open. It's very difficult to quantify how much material it's going to take to construct one of these, because you usually don't have good founding information. You don't know how deep your rock is, but you just can't get out and find that because it's failed. It's also, they have a large footprint, a lot of clearing, a lot of our slides occur in environmentally sensitive areas. And so for that reason, they're problematic. So in 2015, we have what I like to call our pivotal moment. We had been looking into some different strategies to do repairs and different ways to get funding, but nothing had really taken hold until we had an event on Highway 23 in Franklin County. And I was actually in this building. I don't remember what the conference was, but I walked in and my boss at that time, John Animal, said, you got to go up to Highway 23 because there's a slide and it's in bad shape. So that's what I did. And it very much was. So that was the first time we had an independent contractor take a look at a slide for us, and GSI, Geostabilization International, joined me there that next day, and they proposed a slide repair that would have a 7-week time frame, would cost about $400,000 with some support services by our maintenance division. And we did not have a way to execute that contract, and we thought it sounded like a lot of money. So District 4 attempted to restore the roadway with millings. The road was closed in early June. We led a construction project for $1.8 million. The total overruns, $122,000, and we reopened the road October the 9th of 2015. You know, that's a bad thing, but good things come out of bad things. We learned from that. We learned that there were better ways to do things, and we had good, strong numbers to prove that that if we could move quick, we could save a lot of time and a lot of money. So one of the first things we did is we organized a inventory of all of the slide locations in the state. And when we did that, we found there were 230 locations that we could find, and 152 of those were affecting the road or the shoulder, which means they're potential road closures. So we categorized how severe we thought those were with different colors, and we've developed this GIS map. And this GIS map, having this data, is really the key to the whole program, because in state government, you have to be able to prove that you have a need to get the tools to fix that need. So this really is the backbone of the whole thing. So each one of these locations, we have different information. We got the location information, any environmental concerns that we know of, utility concerns. We also, in this database, have at least 1 or 2 photographs of the area, and then a sketch of what's going on. And that's our starting point for every slide. So we also learned a handy little nugget of information. A gentleman named Pritesh from Federal Highways has been a great asset in this program. And one thing he told us was, hey, a slide doesn't have to be created, and it doesn't have to be catastrophic to qualify for ER funding. It just has to be affected by a qualifying ER event. Handy nugget of information. So in 2015, there were 2 events. We had our database of where our most critical slides were, and we had a guesstimate of how much those would cost. So we asked for funding for those, and we received $24 million, almost $25 million. So that's what I thought when they called and told me that. Tony Sullivan, assistant chief at that time, says, "Oh, I got great news, great news. You've got $25 million to work on slides." And I said, uh-oh, Paul's in trouble, bitten off a little more than he can chew here, because now we've got to do $25 million worth of work, and didn't really have a good means to do that. So we established some on-call repair services with Geostabilization International, Hayward Baker, who is now Keller, and Hinkle Environmental. And since then, we've added some on-call rock buttress repairs very recently, contractors. So if that is the correct method, we can do that also. But this gives us the ability to move quickly. And that is the key to repairing a slide. If you can stabilize one before catastrophic failure, the cost is going to be about 10% of after. We've got plenty of numbers to prove that. So I'd like to talk through a few of our case histories here and introduce some of the methods that we have used. So public enemy number one was what we call the Ozark slide. It's on Interstate 40, just north of Ozark, Arkansas. And it is a dandy. When they called us out to look at this, the district called us and said, hey, the Ozark slide's been going on for decades. We're seeing a lot of movement here. So when my team went out, we observed a 6 to 12 foot vertical drop that was not very far from the interstate. This had worked its way up from the bottom, and catastrophic failure was imminent. It was going to happen. It's not a matter of will it happen. It's a matter of when is it going to happen. So this is one of the first ones that we really got to work on, and it was a mess. Shoulder cracking. This slide from top to bottom of the slope, there's dips and heaves all the way down that slope. So what you're looking at there that just looks like an embankment, that's earth that's been heaved upward. Pretty impressive. And what happens when you get a big heave like that is normally you build a pond is created behind it. It's landslides are one of those things that just feed off themselves. And this was no exception to that. The most impressive feature of this, I don't know how well you can see it there. I can see it real well on my screen. And if you got any landslide nerd in you at all, you're going to love this. So what you're seeing here is an area at the very toe of the slope where the ground is heaved upwards, but there's a stream that cuts through that heave. And you can see this ditch, it's about 6 feet deep. It's about as tall as I am when you're down in the ditch. So you would think that that would be a stream that collects a large area, maybe runs for a few miles. It starts at that spring right there that is maybe 50 feet from the previous picture. So this thing has a tremendous amount of water going through it when it's a big rain event. It's really, like I said, if you got a slide nerd in you, that's pretty cool. Just another picture of that. Another interesting feature that this slide has, got a pointer here, is this little tail right here. Okay. 95% of the slides that we look at, if they cross the road, they cross in a circular pattern. So there's a crack and a return crack. And this is one of those oddities where it just slices across the road. And what we've learned is that is a telltale sign that there's a significant differential under the ground there. And in our borings, we've noted that on one side of that crack, the right side of the screen, the rock line is about 8 feet deep, and on the left side of that crack, it's about 45 feet deep. So very, very significant slide, very significant differential. Anyway, okay, so the plan we came up with to tackle this slide was an anchor block and cable retention system. So for this system, the contractor drills into the ground, anchors the cable with concrete, and then puts a big concrete block on the slope. The cable is tensioned, the block gets pushed into the slope, and add stability. So here's some
Right.
pictures
Okay.
that while it's underway, they're drilling
So, I mean, can you just,
with this big awesome drill. Here comes the cable. The ants go marching down and put that in. It's grouted in, and then this hydraulic jack pulls against the cable, pushes the block into the slope. And that's kind of what it looks like when you get done. So we did 3 rows of that. Everything modeled out wonderfully. Great idea, just brilliant, really, except that it didn't work. Didn't work very well at all. I would say that it probably saved the interstate. It kept us from having an interstate closure, but the crack came back. So this is about 8 months after that repair was complete. And there you go. So it's time for plan B. Bought us some time. And time is very valuable if you take advantage of it. So we said, what can we do to really find out all the information possible about this slide? We did a very extensive drilling program. We installed a lot of inclinometers, and we also took advantage of some geophysical testing that we had recently learned about through one of our research projects, TRC 1803. So we teamed with Clint Wood from the University of Arkansas, and he performed a plethora of geophysical methods. And that, we just learned a tremendous amount from that. So now we know where the water is, we know where our soft material is, we know where our bedrock is. Part of that is mapping the actual bedrock in a 3D manner. Another very unique feature of this slide that we found through this subsurface mapping are these humps and depressions in the bedrock at the toe of the slope. Now, I don't know how that got there, but what it causes is a rigid area that holds water. So we're holding water under this area, in this area. This always stays saturated. Our load from up above pushes that down and up over this rigid area to another soft area. We didn't have a tremendous amount of right-of-way down at the toe of the slope. There's actually a very big high-pressure gas line at the toe of the slope. So, you know, first thing we look at is, can we drain this area? No, we cannot. So in slide repair, you generally either take away a driving force or add in strength, one of those two. And in this case, we did both, and we tried to take advantage of the strong area. Red doesn't show up very well on red. The strong area and unloading the soft area. So here is plan B on the Ozark slide repair. What we did is up here in this area, we added soil nailing to add strength in with our cables and anchor blocks. And these are 30-inch drilled shafts. They're on 7-foot spacing. They're socketed into rock, and they've got a cable tieback at the top for lateral stability. We also did a very large excavation in this job, and that really is key, because now we've taken load off of this soft wet area. And if the material down low doesn't move, it doesn't pull all of this with it. So we've added as much strength as we can possibly add. We reduced our driving load, and knock on some wood, so far that's been a successful repair. It's something I'm really proud of. We were in the road for maybe a week during all this repair, so no impact to traffic, no significant impact to traffic. I suspect it will settle at some point in the future because there is such a differential, but I would say that our threat to catastrophic failure, losing the interstate, is close to zero. And that's, so there's a photo of what it looked like when we were getting close to completion, a lot of concrete. Okay, so another method that we've employed to repair some of these slides is conventional soil nailing. And we like to use self-drilling nails. And this is an adding strength type repair. So we're on a downhill slope. These hollow bars get drilled in. They get grouted through the center of the bar, around the annulus, and it adds strength to the area that you need to add strength. Also, a very low impact to traffic, very low environmental impact type of repair. We've had a lot of success with that. So this is kind of what the finished product looks like here. Everybody relates the gunite finish or the shotcrete finish to soil nails, but it's actually the nails that are behind that are doing all the work. And the shotcrete face is just for stability on this outside of the wall. There's another one of our soil nail repairs, same kind of construction. So when we want to do soil nails, but we've lost a little too much of our roadway, we'll do a build out type repair. And this is the situation where we had that very scenario. Bedrock was really deep. We felt like a soil nail repair was a good call on that, but we needed extra room, extra driving room. So we do a soil nail on the material that we've got, and then we do a build out. And we've used two different methods to do these build outs. One of them is a gravity block wall that sits on a grade beam. So if you can imagine it, I know it's a little bit of a stretch. I don't have great pictures. I'm about as good a photographer as I am a presenter. Behind this is a soil nail wall that retains all the load. So the gravity blocks have very, very little load on them. Another thing we've done is a GCS build out. So a few years back, Federal Highways had a big push to build bridge ends out of geosynthetically confined material. Well, we do the same thing on a slide repair build out when we need a little extra room. So that's one of my favorite before and afters on a soil nail job. Pretty good stuff. All right, so that brings us to my favorite type of repair. I call it the drill rail method. If you've got PhD behind your name, you're gonna think I'm an idiot and this is a bad idea probably. If you grew up on a farm, you're gonna think, that guy's a genius. How did he come up with that? Well, I borrowed it from my friends in Kentucky. So what we do here, we have a drilling rig that is powered by an enormous compressor, and this rig has the ability to drill through almost anything, create a 12-inch diameter hole, 40 feet deep, and they can do it on the pronto. It does not take long at all for them to drill a hole, even in pretty hard material. So once that hole is created, a winch line's run down from the top of that rig and picks up a 40-foot section of used railroad rail. Railroad rail goes into the hole. Some of this failed material is excavated, and they create a sheet of cribbing out of used guardrail, which we dispose of hundreds of thousands of feet of that every year. Then we backfill the excavated material with clean rock wrapped in fabric. This is the fastest, cheapest way to fix a landslide. I wouldn't do it on an interstate or US highway probably. But most of the places that we have slide issues, it's a fantastic method. So this is the first place that we tried this method. That's White River in the background there. So super environmentally sensitive. And it's where White River runs from east to the west. So the river doesn't even run the right direction in this place. 1 week later, that's what we had on our first drill rail repair. Pretty awesome stuff. Here's a couple more before and after. This is Highway 66 going into Leslie. Really nice repair. Super low footprint, super fast, recycled materials, relatively inexpensive. Good stuff. Now we still do some rock buttress repairs, and unfortunately don't have very many good pictures of those because I don't like them as much, I guess. But anyway, some of the slides we get into are above the road, and those are a handful, and normally rock buttress is the way to go with those. This is an illustration of one at Snowball. We were about 1,600 feet from the road. The whole mass was moving down the hill a couple of years ago. There's some aerial pictures of that. It's just an example of some of the things we have to deal with because people normally don't relate Arkansas with landslides, but we do have them, and some of them are good ones. This guy's making its way down the hill with me, and I always like this. It says, I know what's wrong. WATTS. That's an old political bumper sticker. I know what's wrong too. The hill's coming down in the road. Anyway, that's a good candidate for a rock buttress. Also one where we've got complete catastrophic failure. That's another good candidate for a rock buttress. And that's what we did on both of those jobs. But let's see. Yeah, it's another example of that. So how much progress have we made? The little blue dots are repaired slide locations. That's all been done since 2015. And most of those will have 200 or 300 foot slide repairs in them. So I would say pretty good. We've made a pretty good dent in our map. We've repaired over 28,000 linear feet of failing slopes through this program since 2015. And I don't know what the total number is because I got tired of counting at 28,000. But anyway, so that's what our map looks like now. Those are our repaired locations, and we have money from a couple of funding events that we're working on. So yellow dot, red dot is a funded slide. We're trying to put the repair plan together for now. And then the blue dots, that's the happy dots. That's the ones we're done on. All right. So that concludes my slide part of the presentation. Has anybody got any questions about that? That's a good question. So yeah, sure. Okay. So the question was, why would a PhD dislike the drill rail method? It's because it doesn't model out nicely. So the standard for modeling, geotechnical modeling of a landslide goes something like this. You go out and you drill and you determine the properties of the subsoils and you put that in your model. And then you reduce the strength properties in your model until you lose your factor of safety. So your model says it's failing. And then you design your repair to bring your factor of safety back up. So you take what you know and you manipulate it into something that you know is incorrect, and then you bring it back up to something you feel good about. The problem with that is most of our slides have firm material, and a very, very thin layer of soft, slick material on top of bedrock. 75% of our slides have that configuration. The drill rail method creates a shear connection between the good material on top and the good rock on the bottom. And that is very hard to model. So if I say a PhD or even a typical geotechnical consultant would have a hard time modeling that and justifying their geotechnical work. So that's why I say that. But proof's in the pudding. All right. Any other questions?
Okay, any question from Zoom? If there are any questions from Zoom, please unmute yourself and speak up.
I think so.
Okay, super, yeah.
Am I sharing here?
Yes, you are.
Very good, very good. How about that? Perfect. All right. So, asphalt balance mix design. Just want to touch on a few things, here this morning, because I can see a trend that's going to change the way we design asphalt across the country, and Arkansas will be part of that, to a more balanced mix design. So we're trying to find the balance between cracking and rutting. So where we are now, we have adopted the super pave asphalt mix design along with most of the country. So I guess we're rocking on about 20 years of super pave. And some of the key components of and good things that it has brought us are performance-based binder specifications, volumetric mix design and analysis, and the gyratory compactor. So performance graded binders, most what we use is 7622, 7022, or PG 6422. So what that means is when super pave came along, the liquid asphalt companies had to produce material that was rut resistant in a certain temperature range. So if you're using a 6422, it has to be formulated to be rut resistance in a range from 64 degrees C to minus 22 degrees C. So that was a good thing. Gyratory compactor came along. It compacts the material, simulates field conditions. It's a good test. And from that, we do volumetric analysis to determine the optimum moisture. All right, I'm sorry, I'm a soils guy, not the optimum moisture, the optimum aggregate structure. And these are the material properties that the department specifies when dealing with an asphalt mix design. And one of those I want to highlight is the, my thing doesn't change, so I've got to look at yours. Wheel tracking test or rut test. So the rut test, it's performed as part of the mix design verification project, mix design verification process. It's performed in the materials division, and we have an APA junior. So we're testing every mix design at the mix design level for its rut number. So how does this compare to what we might be seeing or probably will be seeing in the future? Superfave brings in performance graded asphalt binder. The balanced mix design is based on a performance tested mix. A little different there. And one thing that's introduced with the balanced mix design is a crack test. We have gotten very, very good at producing asphalt that does not rut, but we have premature cracking in lots of places with lots of mix designs. So this test is aimed at addressing that issue. Couple things you get from the ideal CT test or crack test: load versus displacement curve, displacement versus time, and the CT index. That's the key number. So the definition of CT index from Humboldt: a function of the total fracture energy of the slope of the post-peak curve at 25% reduction of the peak load. Y'all understand that, right? So I could explain to you in scientific terms what that means, but then none of us would know what it means. The CT index is the sweet spot where your AC and your load match up to reduce cracking. I didn't explain it very well. We'll show it on the curves. So we're going to start with our rut test and plot that. And that gives us a boundary of the AC content where we don't anticipate to have rutting. And then we add a right axis to plot the results of our ideal CT. And we're looking for the sweet spot
the ideal CT number or CT index where we don't anticipate rutting. And we designed based on the AC content in between in this zone right here. So if we've got our AC content in this zone, we should have a good basis for this set of aggregates to have a mix that won't rut and won't crack. That's the idea. So the design philosophy that we are trying is from the National Pavement Association, Approach D, and be lovely if I could see this on here. Bear with me. Okay. So this approach, you select an initial aggregate gradation and your binder grade for the temperature ranges that you're going to design in. Conduct rut test and crack test for 3 or more binder contents. When you're happy with that, you select your optimum binder contents and mix component proportions. Conduct moisture damage testing. When you're all happy with that, you get a job mix formula. So this job mix formula, the volumetrics are no longer based on, we tell you, here's what your volumetric numbers will be. The volumetrics will be arranged based on the optimum set of volumetrics. Okay, I broke it now. Okay. No, you don't see that, do you? Well, now I can see it and you can. Can you advance that slide for the screen? That's okay. I can talk you through the rest of it. That's all right. There's no good illustrations here left. It's no problem. There's no problem. Just got a couple slides left and maybe I can talk you through those. Okay, so we've got our volumetrics. An example of that, instead of saying your air voids shall be 4 plus or minus 1%, the optimum air voids for this mix design may be 3.6. So our specification may be your air voids are the optimum plus or minus 1%. And that would follow through for all of the volumetric properties, including the gyrations. We're looking for an optimum gyration instead of a gyration number. So where we are now, RDOT is currently performing ideal CT on our current mix designs. So we're taking mixes that we've got a pretty good feel for how they've performed in the field, and we're performing CT testing on those to see what the correct ideal CT number we're looking for. So we're trying to determine the best number to set that left goalpost or vertical line from the previous slide. We're working with producers to develop new mix designs. We want to bring in mix designs as early as we can, so that when implementation comes, everybody's ready for that. And we feel like it's possible that we may be putting mix with this design method out by the summer of 2023. That's kind of what our goal is. So that's all I've got in regard to that. Has anybody got any questions? I hope not, because I'm not an expert.
Do we have recommendations from the University of Arkansas on the research project on the allowable variations on the volumetrics for our acceptance criteria? Is that something you're developing from the research, the field applications you're doing?
Yeah, that's a good question, Dave. So at this point, we do not. It's something we will develop as the project goes along. And I think that's going to be a moving target on some things. So I suspect it will be what ranges we're going to accept, plus or minuses. And I think we're going to have to put some mix down to know if we've got those numbers right. So that is part of the research project. Before we put mix down, we'll have numbers we feel pretty good about. And we're not the only state that's doing this. So we're also looking at other states and what their ranges are. But at this point, the answer to your question is no, sir, we don't. Thank you. Sure.
Because of the time constraint, we may be able to get one more question. If there is none from the room, do we have any questions from the Zoom? If so, please unmute yourself and speak. Very quiet group, looks like.
That's a good question. It's my favorite question today.
All right, okay.
I have one question for Mr. Tinsley.
Can you introduce yourself? Tell your name and your organization.
Yes. Hi, Mr. Tinsley. Thank you for the wonderful presentation. And I am from Benton, Arkansas. My name is Kazi. I work for Hope Consulting. So we mainly work with land development and site design. So it's not directly related to your presentations, but as you were the head of the material division, I would like to ask you one question that recently, in some projects in the West Arkansas, so we are getting some city comments on our project that we need to have permeable pavement for the parkings and some driveways in a certain portion. But when I went back to RDOT standard or city standard, I didn't find anything on permeable pavement, and they really are making us to have something permeable in our parking. So one option can be the permeable flexible pavement like asphalt pavement, and another is the having permeable blocks, which is really expensive for the owners and the clients. So do you guys have any plan to do anything on this permeable pavement in future, like any research project or anything else, even the contractors, any asphalt contractors from we have contacted many contractors around that area, but nobody have done anything like that. So I don't know, if you have anything in your mind on this.
So we have done some permeable payments in the past. That's definitely not the direction that we're going in. My opinion on it, I wouldn't do it unless I was doing on-site underground stormwater retention. And I don't think anything in Central Arkansas has a high enough value dollars per square foot for real estate to do that. Anyway, that's just my opinion. To help answer your question, there has been a lot of research done in that area. And if you would, I'm not sure the best way to contact one of us, but
I know
we could.
I know Tamzit, so I can
Perfect.
get both of
Perfect.
you connected and
Yeah, we can
see
get
the
you
right people,
connected
yes.
and get you plugged into that.
To add with that, I was looking for Mr. Alan Meadows. I know he delivered a presentation at a state on permeable pavement, concrete pavement. So he just stepped out. Tamzit, so I will, Mr. Alan Meadows from SCPA. So I will give him your contact information, so he will get in touch on the from that ACPA perspective as well. All right.
Okay.
Thank you.
Thank you.
Thank you, Mr. Paul. Appreciate you. All right. I want to see like that. Wow. Actually, he's on the screen. That's my one of my elder brothers, Mr. Abu Al Hussain, and I am still his baby brother. So whenever he is not an engineer, but he's a retired secretary from the government of Bangladesh. So when we have any conference or anything, I send him the link and he attends my conference. He just want to see how I am doing. So hopefully I am meeting his standards. So I appreciate, brother, for you staying up so late and listening to this conversation. And I'm always grateful to him. I just wanted to say that in publicly as well. Hopefully he can hear, but hope he did not want to sleep by putting his screen on. Anyway, so our next presenter going to be from Federal Highway Administration. Can everyone see the screen? Zoom and Zoom. Okay,
Yes.
thank you. Yeah. Next speaker is Mr. Michael Powell, and he is the senior concrete engineer in the Federal Highway Administration's Office of Pre-Construction, Construction, and Pavements. Mr. Powell leads a variety of Federal Highway Administration and initiatives in the areas of concrete materials, concrete construction, and quality assurance, including the FSWA's effort to implement performance specifications for concrete. Additionally, Mr. Powell manages the FSWA Mobile Concrete Technology Center program, which works to implement new concrete technologies throughout the country. Mr. Powell holds a Bachelor of Science degree in Civil Engineering from Clarkson University, a Master of Civil Engineering degree from Rensselaer Polytechnic Institute, and is a licensed professional engineer in the state of Maine. He has 2 grown daughters and lives in Augusta, Maine, with his wife, Jody. Please help me welcome Mr. Michael Powell to deliver his presentation. And Mr. Powell, I already made you a co-host, so you should be able to share your screen.
Okay, let's give this a shot.
Yeah, we can see you and we can see that you are sharing your screen. Okay, perfect. We can see your screen. Go ahead,
Okay,
Michael.
the cover slide showing now?
Yes, everything is perfect here in the room.
Okay, all right. Well, thank you very much for the opportunity to present today. Sorry I can't be there in person. I had a personal commitment, so I couldn't travel this week. I always enjoy coming to Little Rock. I was just there in August to speak at the concrete conference, and I was looking forward to coming back. So I'm sorry I couldn't make this one, but hopefully you'll still get something out of the presentation. I think I've got some good information to share, and we'll start out by talking about our Mobile Concrete Technology Center and what that program's all about, how we interact with practitioners, and maybe some tools or products that we have that might be of use to you. And then we'll talk about performance engineered mixtures and kind of what we're doing to support it and what's happening nationally with implementation. So if you're not familiar with the MCTC, this is what it looks like. It's a self-contained concrete laboratory on wheels, and we're funded by this specific program. And each year Congress gives us a chunk of money. And the nice thing with our program is Congress is not overly prescriptive, and they tell us basically go do good things for concrete and then come back and tell us what you did. And they decide whether or not to continue to fund the program. And this program, along with its sister program, I have an asphalt trailer, Federal Highways does, that's been around for over 30 years. So we think we've hit on a pretty good way of getting things done. But what makes our program unique is that we evolve to meet the stakeholder needs. So the things that we're working on today, which are largely the performance engineered mixture initiative, is very different than what the program emphasis was about 10, 15 years ago. where we worked very heavily with the development of the MEPDG design guide. So we stay relevant, again, by evolving to meet stakeholder needs, and hopefully you'll see some of that with some of our products here. This is our mission, and I think the graphic really covers it best, is that our job is to identify new emerging technologies that are very promising for practitioners and get them into the user's hands. And whether it's new technologies or underused technologies, again, our job is to help the agencies and the industry advance concrete technology that's being used on our infrastructure projects. You can see through some of the bullet points, some other things that we do. We work with states on their specification reviews. We do training and other technical assistance and some troubleshooting. And if you're not familiar with our program, you might think that because we're a federal government program that we target our efforts at the states, and that's certainly true to some degree, but we think of ourselves not necessarily as pro-agency or pro-industry, that we're pro-concrete. And so we do whatever it takes, again, to help the agencies and industry get better concrete on our roads and bridges. These are the things that we do in our program, and I really highlighted the first two because they're really the backbone of the program. The upper right picture is a picture of us out on a project, and we take our trailer and we set up at the state's invitation. We set up on an active construction project, and we test the concrete. And our testing has nothing to do with the quality of the concrete. We're doing the testing to demonstrate these new technologies, because it makes a whole lot more impact if I can show Arkansas DOT and Arkansas contractors, how these technologies work with your concrete. That's a lot more effective than telling you how good they were when we were doing a project in Oregon. And in this project in the upper right, the gentleman who's squatting down with the white hard hat in the middle, that's my lead technician, Nikolai, who's demonstrating a super air meter. And this is on a project in Colorado. So we get out there for 2 weeks and we test your concrete, and we look to see which technologies might be most applicable in that state. And then we go away for a bit. We do some longer term testing, and then we come back. The picture on the bottom is our quality workshop. We did one several years ago in Arkansas. We were on a project in Arkansas in 2017, and we did a workshop. And I'll touch on the workshop here in just a minute, along with a couple of these other things that we do. We see we get around quite a bit. The green states are where we have been to construction projects since 2008. And here in another week, we will be able to color in South Carolina. We are headed to a project in Columbia for the next 2 weeks. So we will get them. So we don't have too many places left to go. So we get around quite a bit. And that relates to some of the things, the tools that you'll see we produce in the program. This is coming out of COVID. Again, we're the Mobile Concrete Technology Center. So we were not mobile for a while. And I kind of wondered, how fast we would be hitting the road again. But the left-hand column, the states at the top, those are places that hosted us this year. The asterisks at the bottom are states that have committed to a project with us for next year. And I'll be surprised if we can get to all of them. Usually we can get to 5, maybe 6 if paving schedules and placement schedules work out just right. But I'm pleased with the level of interest, and we'll certainly be getting out and about next year. And similarly, on the right-hand side, there's a number of conferences and other activities. The ones without the asterisk are things that we've done in 2022. And then the 3 asterisks at the bottom are conferences that we've got lined up for next year. So the paving process workshop, the quality workshop I mentioned, when we get done with our visit, we do our data analysis and our spec review and the other things associated with our visit to a project, we come back with a free 2-day training workshop that we like to have about 15 industry folks and 15 agency folks. And again, the whole purpose of this workshop, and the reason the state invites us to come and do what we do, is the state's looking to make changes to their concrete specification. So we set up our testing plan on the project to help develop data to generate some suggested changes or improvements to their specifications and practices. And this workshop is designed to sort of work towards a performance specification, again, using the technologies that make sense in a given state. And the goal is to come out of that workshop with the state having an action plan on how they want to move forward. And I'll share one state that moved forward with an action plan. This is certainly our biggest success story. We don't often get this kind of direct comparison right away, but we went to California in 2019. And typically when we go to a state, we'll visit one project and we do one open house and one workshop. Because California is so big and there's so many people we had to kind of contact, we did multiple efforts, as you can see in the first bullet. But Caltrans identified several parts of the spec they were concerned with and they were looking to upgrade. So we developed our test plan for the project, the technologies we thought would fit best. And when we got done with the workshop, Caltrans and their industry, they formed a working group to rewrite part of their specification. And they asked us to participate on that working group. As part of that effort, we gave them some suggested specification language. And they adopted it right away. And the first project that they put this on was a $400 million project in the Los Angeles area. And they bid the project in 2 phases, approximately equal, and the concrete work in each phase was identical. And so they wanted to use this as kind of a head-to-head comparison to see the impact of the specification changes. And the specification changes that we recommended, they compared the bid prices from the first part where they did their existing specification to the updated spec, and they saved $9.4 million in their bid cost. And again, that was the Caltrans analysis of this. And then and not only was this a dollar savings, they're getting a better quality concrete as well. It's a better mix design that they're achieving this savings with. So that's an ideal scenario, but it shows the kind of impact we can have. But I will certainly readily admit, not every state saves $9 million the first time they encounter us. But we do spread the good technologies. We have an equipment loan program. We loan equipment free of charge to anybody and everybody. Have about a $500,000 equipment inventory. And again, we're an implementation program. And so I can come and talk to agencies or industry folks and tell them how good some of these new technologies are. They might be reluctant to invest $5,000 or so to buy a new piece of equipment if they don't know, if it's relevant for them and what use they could make of it. So we'll loan it to people. You can try it for 6 months, 8 months, a construction season, a year. And the only thing we ask is take care of it, ship it back to us when you're done, and share your thoughts on the technology after you've had a chance to use it. And we've had pretty good luck with this program. In fact, just about 3 weeks ago, I had a Pennsylvania contractor return a surface resistivity meter and say, we're done with this. We don't need to borrow it anymore. We just went out and bought 3 of our own. And that's the kind of thing we're looking to accomplish. So if you're interested in borrowing any of the technologies, our website, I'll show you in a little bit. You can go there, see what equipment's available, and reach out to us. Through COVID, again, if you look at the MCTC is the Mobile Concrete Technology Center, and we obviously were not mobile through COVID, so we had to figure out a way to still get our message out. And everybody has their own webinar these days. We do things a little differently. And I make this invitation to anybody listening to this. We will do free training, but what you don't see from us is next Tuesday, we're going to do a webinar on maturity. And here's where you sign up. Because we're an implementation organization, we want to work with an individual DOT or an individual contractor, because we don't just talk about the technology, we talk about the technology and how it's applicable to you. So it's not always as effective if we have multiple states in the room from that perspective. Again, we prefer an individual audience. If you're not familiar with dealing with us, it may be a little unusual to say, hey, federal government, I want free training next Tuesday at 2. But that's what we want. We have equipped the trailer to broadcast from anywhere in the country. In fact, next week when we are on our project in South Carolina, I think we have 3 hour-long webinars set up with an Arkansas group that I showed this same slide at the conference in August. And there were some folks who were interested in some of these. So the bullets that are on the screen are the topics that we offer these trainings in. They're about an hour long. All we need is an audience. And if you tell us who the audience is, we can sort of customize the message. We've delivered these to engineering audiences. We've delivered them to technician audiences. Where we go through when we can take the equipment apart, show how to maintain it, and that kind of thing. The states in blue are states where we've had these virtual sessions, and don't necessarily take that to mean it was the state DOT. For instance, in North Carolina, there was a contractor that we had worked with on one of our site visit projects. He had some turnover in his QC staff, and he asked if we would train 3 of his new QC technicians in some of the technologies that we showed them when we were on the project. So we did a webinar for 3 of his QC staff. Conversely, in Vermont, we had about 150 people on. That was an industry association sponsored event, and there were multiple states, universities, private labs, contractors. So, we will do presentations for anybody that's interested. This is another thing that grew out of COVID, looking for ways to continue to reach our audience. This was actually the industry folks in Ohio wanted to start to expose the industry as well as the DOT to some of these new technologies. But Ohio didn't have a good project for us to visit with the trailer. So we set up what we call this technology tour, which we went across the state for 2 weeks. We hit 6 cities, we did 13 sessions, and each session was about an hour and a half in the classroom, which you see the top 2 pictures, and then an hour and a half demonstrating some of the new technologies and showing what these new concrete tests look like. And again, those are available upon request if your state's interested in something like that. We have scheduled another one for this coming year already, and our calendar's filling fast. Because we get out and around as much as we do, we see a lot of concrete trends and get exposed to things before maybe most of the concrete community does. And whether it's the type of questions we get in our workshops or in conference settings like this, or other data that we see come from our trailer visits, when we get enough information, we put together a one-pager. And the purpose of these is we don't try to answer all the questions about a given topic, but they're pretty narrowly focused. And we say, hey, here's an issue that we're seeing. Here's the reasons why it's a potential issue, or you may want to look into it. Here's some possible solutions. And then most importantly, we provide some sources to go for additional information if this is something that does impact your program and you need to dig into it some more. This is one example, and the data that's on this chart, the horizontal red lines, 3,000, 3,500, and 4,000, those are the acceptance specification limits for strength in these states. And the test results, the blue, obviously 7 days, the pink 28, and the green 56, those are the compressive strengths. And you can see that the compressive strengths we're getting in practice are much higher than we need. And Dr. Peter Taylor at Iowa State is one of my favorite sayings about strength, and it's how much strength do we need with concrete? And the answer is just enough. That if we need 3,000, 4,000 isn't better, and 5,000 is not better than that. And we've relied on strength for too many years to be sort of a surrogate for durability. That if we add good F prime sub C, we must have a good durable concrete. And now we know that's not the case, and I will touch on that some in the second part of this presentation. So what we did when we saw that data, we said, well, we've got some ways to address this. How can we help to optimize the cement content in our mixes and get some of that down? And I put FHWA's sustainability logo on this slide because when we put these 5 bullets together, I am not on our sustainability team, but I do work with those folks. And I asked them about this, and they said, we support each of those bullets. All of those are good from a sustainability perspective. And I know sustainability is certainly getting a lot of airtime, is a high publicity thing these days, but I think it just boils down to good concrete engineering, whether we call it performance engineered mixtures, sustainability, or anything else. Just good concrete engineering is good concrete engineering. And so again, being an implementation program, we said, well, what can we do to help this issue? We looked at the second bullet about optimizing gradations, and we developed a spreadsheet. And this spreadsheet, if you shoot me an email, we could send it to you free of charge, and you can play with it some. We put this together. You put in your aggregate blends and your aggregate gradations, and this spreadsheet will spit out. The lower left is the Shillstone workability chart. The upper right is the tarantula curve, and the lower right is the 818 chart. And we can see if we have good workable mixes. And as you can see here, we're out. So it's as easy as switching the blend numbers a little bit. And now we're still a little bit out. Switch the blend numbers again, and now maybe we've got a pretty decent mix to work with. So we can save a lot of time from trial batching, again, just by doing a little paper exercise. And if you are someone with the industry, I'd be glad to send you an unlocked version of this so you can add a cost module to this so you can see the cost impacts of adjusting your aggregates. We're not a research program. Yeah, again, we're an implementation program, but we do work with the research community. And this is one test I wanted to show you that is not a standard test yet. This is still being developed. It's being developed by Dr. Tyler Lay at Oklahoma State University. And it's called the float test. And essentially what this is Dr. Lay has shrunk down a bridge deck placement into a test format. And you fill that box on the upper left, you fill that with concrete. And then the upper right, you just kind of screed it off with a 2x4. You don't vibrate it. You're not looking to compact it here. And then you take and punch some standard holes in it, 1 inch deep, 1 inch diameter holes. And then you see how many passes it takes to finish those holes away. And if anybody's ever been out on a bridge deck, that's the most applicable use for this kind of test, that we want to be sure we've got a good workable bridge deck, because if we don't, then we end up with the contractors having to put extra water on it to close the surface, and we get delays in placement of our curing techniques, and a lot of bad things that happen because we don't design our mixes to be workable. And we've relied on the slump test as to be an indicator of workability, just like we've relied on compressive strength to be an indicator of durability. And again, neither which is the case. So, and there's a scoring sheet, and you see how workable a mix do you have. And with that, that's what I've got to say about as an introduction to our Mobile Concrete Technology Center. There's our website. Stop by and take a look. We've got a number of other tools. There's some instructional videos on a number of the technologies and other things. So, and certainly reach out to us at any time you've got concrete questions. With that, I want to shift gears a little bit and start to talk about performance engineered mixtures. And if we look at concrete testing, this year the slump cone is 100 years old. And if you look on the lower left, you see what cars look like 100 years ago. And then we move ahead to the late 40s, and we got the type B pressure pot, and cars had evolved some. And then in the early 80s, we got the rapid chloride test, and cars had evolved to the Ford Pinto. And that's where concrete technology has stopped evolving as far as agency acceptance programs and in general what we do for QC programs. That's the end of the technology. And I say, how many people still drive a Ford Pinto? We haven't evolved our technology as we've evolved the rest of the concrete world, because we're horrible with change. In the 1980s, we figured out that it's good for our concrete to use supplementary cementitious materials. And the Romans had figured that out 2,000 years ago. It just took us a while. 28-day strength testing, I'll talk about in just a second. And again, the slump test. The slump test doesn't tell us anything about the quality of our concrete. And we have over 40 states in the country that use it as an acceptance test. And to those agencies that do, my challenge is, show me a project that failed prematurely because the slump was an inch out and didn't meet spec. Or another example that I'd use is most agencies' bridge deck specifications call for 2 to 4 inch slump. Well, let's say we have a 4-inch slump, but it's a straight Portland cement mix. And now we come in and take 20% of that cement out and put in a fly ash. So we've made the concrete markedly better from a performance perspective, but now the slump went from 4 to 5 inches, so it would be rejectable under the spec. So I think we really need to revisit the slump test. The slump test, again, was developed 100 years ago for the concrete we used 100 years ago. It is not applicable for acceptance testing for today's concretes. And the Great 28. So we'll mention 28-day acceptance testing for concrete. We test concrete for strength at 28 days because that's where we really get the strength gain curve for Portland cement to flatten out. But again, those are not the mixes we use today. Now we take out 20, 30, 40, 50% of the Portland cement and replace it with a supplementary material. All of those supplementary materials take longer to develop their performance properties. So we've changed our material, but we haven't changed how we evaluate it. And that's why we get the strengths that we do. And we look at how do we accept concrete. These are the tests we accept with. Those are pretty common tests that we see around the country. But what message do we give our concrete industry? Is we adjust price based on strength. The concrete industry knows that, yeah, they need to get all their other qualities right, but they know the big hammer and the big penalty is going to come if they don't make their strength. So we get strengths like what's in this table. And I am fortunate. I still get to live in Maine. My job is based out of Washington, D.C., but I get to live in Maine. And I was doing some work recently with a fellow New England state, and they have a 4,000 PSI specification. But if they get a cylinder that breaks at 3980, it's a 50% pay reduction. And they routinely get over 8,000 PSI strengths. And this is, again, not a good thing. More strength is not a better thing. Our practices and the way we look at our concrete hasn't changed, despite the fact that it is a vastly different material than when we developed these testing technologies. So we get what we're willing to accept. We've told the industry we want strong concrete, and they deliver strong concrete, not necessarily durable. And it's how we write our specifications that drives that. Because again, most states rely on strength, slump, and total air content. Strength has no correlation to durability. Slump has no correlation to durability, and total air has marginal relation to durability. But that's where, again, what we've told the industry in our specifications is important. And we need to revisit our specifications and how we tell the industry what we want for a product. And that's what this PEM idea, the performance engineered mixtures, is all about, is to get past the idea that slump strength and total air tell us what we need to know about concrete. We have new technologies, and the reason this can all happen now is the research community has delivered to us over the last decade. They've given us new tools and new tests that we can use and not rely on the 1981 and earlier technologies that we still do. Then we need to look at things like getting prescriptive restraints out of specifications, the minimum cement content. If a contractor can give us good quality concrete that performs like we want it to, and there's 500 pounds of cement in it per yard, why would we force them to put 550? We need what we need. And single aggregate gradation. A number of states have single aggregate gradation requirements. Again, we are buying the combined product. So we should be looking at the combined gradation, which is, again, one of the reasons we developed that tarantula curve tool. And this is what a PEM type specification looks like as compared to current practice. And if we look at option 1 on the left, that's what is very common in the US today, is agencies do not rely on any QC information. In fact, there's only 15 states that even mention quality control in their specifications, and slump strength and total air. That's where specifications are centered around. Versus a PEM vision of what a specification looks like is we do get some quality control information from our supplier. And I saw a TRB presentation this year, and the presenter said, you can't have quality without consistency. And that's really a lot of the core of what PEM is all about. And if we look at the bullets here, the unit weight, if we check the unit weight and that's tracking consistent, we know our physical properties of our concrete are consistent. Calorimetry, we'll check the chemical properties. If our heat of hydration is similar batch to batch, we know that our chemical properties of our cementitious system are running consistently. And the Phoenix is a new technology for determining water content. If we know our water content is consistent, along with the physical and chemical properties, we're setting ourselves up for pretty good chance for success. And then the resistivity test, I don't have time to get into what all these tests are, but it is a new durability test. It is the best test we have today that can be incorporated into either QC programs or agency acceptance programs. And it does indicate concrete durability. We still need to measure strength because it needs to be strong enough. The SAM number, SAM is a super air meter, is the device shown in that picture. And it generates a number that's indicative of the air system in the concrete, not just the total air. So it tells us if we have air that is going to make our concrete freeze-thaw durable. And then for slip-form paving, we like the box test along with the SAM for mixed design approval. And the box test is a workability test that does tell us workability as opposed to the slump test, which does not. The PEM, the states in the blue, along with FHWA and the industry, participated in a 5-year pooled fund that is just starting to wrap up now to advance the PEM principles. The states with the star participated in an incentive pilot program, and I've got some information from a few of those pilot projects to share. In New York, I want to jump to the 4th bullet to start with. It says the second supplier was reluctant to participate. The first supplier refused and walked off the project. They had started this project with their typical Class C mix, and then partway through, they wanted to change over and try this new PEM approach. And the supplier said, no, we want nothing to do with that, and they left. And the second supplier was also reluctant, but the state sat down with them, explained what they were after, and they agreed to give it a shot. And in the end, they agreed that it was a better mix, and the QC requirements were pretty much in line with their current practice. In New York, along with the other states, you'll see training is listed as a big need to, again, training in these new technologies. And in 2023, all of New York's projects are going to be done using this approach, because that 3rd bullet where it says 30% cement reduction, they were able to demonstrate this on that project, and their state legislature has passed some pretty stringent sustainability requirements. And the New York DOT has come out and said the only way we can meet these goals is going to a performance engineered mixture approach with our concrete program. There's some data from their project. And again, this is the surface resistivity testing. If you're not familiar with the test, around a 20 or 21 or above is considered to be a good durable concrete. And you can see on this project, the first half of the job they did with their Class C topped out at about a 12, whereas the mix that we suggested and what they changed to was still improving, many months later, and is certainly above any performance thresholds. In Iowa, this contractor, using the box test, we showed them how they could take 45 pounds of cement per cubic yard out of their mix. I was talking with the producer, and they said, we knew that wouldn't work. We pre-programmed the plant to add cement back in 10-yard chunks or 10-pound chunks, but we never had to. And they paved the shoulder. Then they came back and asked if they could pave main line and jump down to the bottom. This project was in 2019. They did the pilot. In 2020, that contractor got 3 more projects from the Iowa DOT and came back and said, we bid those per the standard spec, but can we do these like we did the experimental job last year? And the state approved it, and they are now rewriting their specification to make PEM and a PEM approach their standard practice in Iowa. In North Carolina, I won't read all these bullets to you. It's the same kind of theme. A lot of these tests, the feedback from the agency and the industry is they're good, useful tests, and we just need some training. And this box test that I mentioned for slip-form paving, the top set of pictures is from the contractor, and they use the box test to help them zero in on a good workable placeable mix. And you can see the different iterations they went through tweaking their mix. And you can see what they started with versus what they ended with. And this, he had never seen this test before. So you can see it is immediately usable. And on the bottom, again, is resistivity testing. The contractor had never seen this test before. The data on the left is from their first lot of production, and the data on the right is from their second lot of production. And just because they started paying attention to this test, running the test, and seeing what their materials were doing, they reduced the standard deviation in this test by over 20%. So just the first time they saw it. And here's some of the feedback from the report they submitted. The contractor said this was another job where they started with their standard mix and made a switch partway through. And the contractor told us at the end, we don't care what the specs are moving ahead. We're going to use these tools and techniques to design our mixes. I think the message is pretty clear that this approach works for the industry, and which is, I think, one of the reasons we see it catching on and spreading more, is it's not something the agencies have to force. That it's good for the industry as well. And North Carolina DOT has piloted a bridge project, and they are currently working on a specification of their own. Similar story in Colorado. We were on a project there with an open house in that picture in 2018. We worked with them on some spec revisions in 2019. Their industry was very supportive. In fact, we took the trailer to Wyoming this year. And when we were having our coordination meeting with the contractor and the state, we started to discuss some of the technologies we would be presenting them with. And the folks in Wyoming were telling us, oh, we're familiar with that. We already do that. We adopted this. And we were a little confused and said, how did you get exposed to all this? Well, the industry association director for Colorado, she also covers Wyoming. And she participated with us when we were in Colorado in 2018. And she helped bring a lot of those technologies to Wyoming based on what she saw in Colorado. So again, I think that really demonstrates the support that industry has for these technologies. Some other states that are interested, again, Pennsylvania, the association director in Pennsylvania approached PennDOT and said, we need a PEM spec for PennDOT. And they currently, back in February, I think they put together their working group, and they are working on their spec. I mentioned Ohio invited us in for a technology tour, and we coordinated with the Ohio DOT on that, and they are currently working on a spec with their industry partners. Same story in Connecticut. They're working on a PEM spec. And then the FAA and DOD, several months ago, I was fortunate enough to be invited to participate on their project panel. Well, they took a look at what was going on with PEM in the highway community and where industry was headed with that. And they said, we need PEM for us. And in talking with those folks, it surprised me a little bit, because the Department of Defense generally doesn't reach out for a whole lot of engineering assistance. Between the Army Corps and the NAVFAC people and their lab in Vicksburg, they have a pretty solid engineering talent group to draw from. But they saw what was going on with PEM, and they said, hey, we need that for us. So they hired basically the same research group that worked with us to develop PEM for highways, and they recently awarded a $750,000 project to develop a PEM specification for runways and airfields. And I mentioned that comment from the TRB presentation about consistency. It's even more important in their world. And we've done some things with how we envision quality control and statistical acceptance moving forward for highways. Say they've taken it up a level. And as they explained to me, if you have a little bit of a consistency problem and you get some surface defects on a highway, you end up with a chipped windshield. On a runway, that gets sucked into $1 million jet engine. So they're very focused on this. I gave a presentation similar to this a couple of years ago at a multi-state conference in the Northeast. And at the end, one of the state folks said, but Mike, you're asking for a lot of change. What's in AASHTO now with this PEM stuff, you're asking for a lot of change. And my response back was, the change has already happened. Let's just go back to 1981. Again, the last time we saw any sort of evolution in concrete testing. And have cements changed since the early 80s? They sure have. And now we use a lot more supplementary materials than we did in the early 80s. Chemical admixtures are changed. The de-icers and things we put on our roads have changed. And the agencies are different. Most agencies are not as big or as deep as they used to be. And concurrently, the industry, the skill set and knowledge base has grown there. So since the early 80s, we've changed our materials, we've changed our exposure environment, and we've changed our people, but we haven't changed our specifications and our technologies. And I think it's the time, and what PEM gives us is a route to get to a way to properly assess modern concrete materials. So hopefully I've piqued some interest in the PEM topic. Although these documents are now 5 years old, they're still very relevant. We put those together at the very start of the PEM effort. They're available free of charge on the National Concrete Pavement Technology Center's website. The first one is about sort of the fundamentals of PEM and what it's all about. And then the second one is about incorporating PEM principles into an agency QA program. These are about 5 to 6 pages apiece, very good reading. And with that, there is my contact information, and I'd be glad to take any questions if there are any.
Are there any questions from the room? Do you have any question from the audience attending Zoom? If you have, please unmute yourself and speak. Thank you very much, Mr. Michael Pearl. Appreciate you taking the time and giving this very wonderful presentation. So let us give a round of applause for Mr. Michael Pearl.
All right, well, thank you, and thanks again for the invitation.
All right, thank you. Okay, next on our agenda is that is going to welcome remarks from our Chancellor. And let me briefly introduce our Chancellor to you, and also make Dr. Shields as a co-host, so he can share if he has any screen, or he can speak. So Dr. Shields, you are co-host, but let me introduce you to the audience. As you know that this is the hybrid mode of the summit. And we have some folks here in Little Rock. About Dr. Todd Shields, and as an academic administrator, a nationally known scholar, and an unabashed champion for students, staff, and faculty, Dr. Todd Shields was named the 4th appointed chancellor and the 14th individual to lead Arkansas State University. Before joining A-State, Dr. Shields served as Dean of the J. William Fulbright College of Arts and Science at the University of Arkansas since 2014. He was previously Associate Director of the J. William Fulbright Institute of International Relations, Director of the Diane D. Blair Center of Southern Politics and Society, Interim Dean of the Clinton School of Public Service, and Dean of the Graduate School and International Education. He led the creation of the School of Art in 2017, following an unprecedented $120 million gift from the Walton Family Charitable Support Foundation, and is guiding the construction, was guiding the construction of the Wingate Art and Design District in Fayetteville. He and his wife, Karen, have 2 adult children, Sevi and Dane. Please help me welcome Dr. Todd Shields to deliver his welcome remarks for this group.
Thank you. Thank you very much. And can you hear me? Can you see me okay?
Yes.
I can turn it up more if you have any trouble, but thanks everyone for having me there today, at least with Zoom. I'm sorry that I'm not there in person. I wish I was. I caught the last bit of that last presentation. It was fascinating. I do hope to meet everybody there soon. Unfortunately, today I'm actually meeting with industries and meeting with donors, and actually Abhijit and others, you'll be really happy. I'm asking for scholarships for engineers. So hopefully wish me luck with that. I do want to thank you all for participating there today and participating in this. I definitely want to make sure to thank the U.S. Department of Transportation and the Transportation Consortium of South Central States, Arkansas Department of Transportation for their continued support. We hope they continue to support this extremely successful group. We want to thank our industry partners there too, Ergon Custom Chemicals, Atlas Paving, Near Ready Mixed Concrete, members of Arkansas Concrete Pavement Association, and members of the Arkansas Asphalt Pavement Association. The Arkansas State Transportation Research Group at A-State, they've had great success in understanding efficient and sustainable use of waste and industry byproducts and preparing long-lasting pavement infrastructures, relying both on basic scientific research and applied research. And I hope you agree with me, they've been incredibly successful in tackling a wide range of problems, solving issues that we're all going to face in the future, and developing the next generation of transportation workforce scholars and even people looking at the asphalt. I just think that they've been fantastic. They have my 100% support. I really wish that I was there today. I want to thank Abhijit for supporting this group, and I want to thank Zahid for inviting me today. Again, my apologies for not being there. I can't wait to hear how it goes. And if there's anything that I can do to help this group in the future, please just let me know. I really appreciate what you're doing.
Thank you, Dr. Shields. I appreciate you taking your time and be here with us. I know you have other engagement at this time. You are probably traveling and doing some kind of other tours. So again, appreciate you very much.
Well, thank you very much too, and wish me luck. The next group I'm meeting with, I'm asking for scholarships for engineers. So wish me luck.
All right. Thank you. Thank you. Have a good day.
Okay. Have a good day. Bye, everyone.
All right. Do you have anything in the chat box? Okay, there is gone. I don't see anything. Okay, so yeah. Okay. Now the next thing on the agenda, so that is going to be lunch break. Unfortunately, we cannot ship the lunch for the remote audience. But what I'm going to do, I am going to do a kind of like, the break room in Zoom. So it will be automatic transfer. So if you want to network with your peer group, and I really encourage and appreciate if the senior person, some of the senior researchers, if you could eat your lunch at the same time, join that break room and talk to the younger folks, so that will give them some kind of opportunity to network with you and know what you are working on and how you have been successful. And same way here, whoever here we are in the conference room, we are going to go outside. The lunch should be ready in a couple of minutes outside. And we have, like, according to your choice, there should be plenty. And actually, I would say more than one per, so it should be multiple boxes. Feel free to grab whatever you like from there, but that would be outside on the hallway. So now let me on the Zoom, I am going to make a couple of break rooms so you can join wherever you feel comfortable. All right, and we will be back at 12. It will be a little bit short lunch. At 12:45, we will reconvene. We'll regroup here for our next technical presentation at 12:45. So please go ahead and enjoy the lunch, and we'll be back at 12:45 p.m. It's about like 50 minutes later, 50 minutes. Okay, so now I'm going to do is that, how do I see the break room? Well, here are the break rooms. So I am creating 3 break rooms, and automatically you will be assigned. Or yeah, I'll let you choose which break room you want. So open all rooms. So you can go whichever room you prefer and join and do whatever you wish to talk with the others. Okay, so the break rooms are open now. Hello, everyone. Welcome back. This is the technical presentation session number 2. And the first presenter of this technical session is Dr. Andrew Bram. Before I introduce you, could someone confirm that you can see the screen, the PowerPoint screen, and hear me well? Okay, I got the confirmation. Thank you. So Dr. Bram graduated from the University of Wisconsin with his Bachelor of Science and Master of Science, and from the University of Illinois with his PhD. He worked with Koch Materials Company for 2.5 years and performed a postdoc at Southeast University in Nanjing, China. He is currently a professor in the Civil Engineering Department at the University of Arkansas, where he has continued to study asphalt emulsions, pavement maintenance, and rehabilitation and sustainability. Please help me welcome my friend, Dr. Andrew Bram. So, Andrew, you should be able to share your presentation file. Okay, yeah, we can see your screen, quantifying pavement preservation in Arkansas. So please go ahead and do your presentation.
Thank you, Zahid. I appreciate it. And I apologize for not being able to be with you in person down in Little Rock. I teach Tuesday, Thursday, so I just finished a class. I got another class this afternoon, but I am happy that we have this virtual option. I'd also be happy to take any questions you may have after my presentation. So please just jot those down and we can move forward from there. So as Dr. Hussain mentioned, I'm going to be talking a little bit about quantifying pavement preservation in Arkansas. Now, I think when talking about this topic, in my mind, it's very important to define what is a pavement's purpose. Now, of course, as I tell my students, a safe traveling surface. If you answer safe to any question, you'll probably get partial credit. A pavement's purpose is to provide a safe traveling surface. Now, it's also important to provide structural capacity for the loads that are being applied. In addition, we want to make sure that a pavement is able to drain water both away from the surface and away from the structure of the pavement. We want to make sure it's able to provide surface friction and a smooth traveling surface. So these 5 are kind of the big 5 on why we have pavements. And all 5 of these are required for proper performance. You can't just choose 1 or 2. It's not a buffet. You really need to have all 5 in order to have proper performance. Now, I like to think of this as an umbrella, and the umbrella is safety. So safety is over absolutely everything that we talk about when we talk about pavements. But then when we think about the 4 other purposes of a pavement, I put structural capacity on one side of that umbrella. And then I put the water drainage, the surface friction, and the smoothness on the other side of the umbrella. And the reason that I do this is because when I think of structural capacity, I think of how thick is the pavement structure and what sort of materials are made in those pavement layers. Now, conversely, when you look at the other 3, I think a lot of these can be impacted by the pavement surface itself. And in my mind, this is a very important distinction to divide these into the pavement structure and the pavement surface. And my theory is, if the structure is sound, and I would like to think the vast majority of the roads that we design are structurally sound, then maybe we should think about how can we take care of the pavement surface. And that is where I'm going to go with in this presentation. And I always like talking about classroom because that's where all the exciting things happen. Students are always saying things and exploring things that I would never think of. And so I'm going to talk about 2 class projects. And these class projects use roadresource.org. So if you've not been to roadresource.org, I encourage you to visit that immediately. And in fact, if you're looking at your phone right now, please just go ahead and go to roadresource.org. It is a phenomenal resource. And I use roadresource.org in 2 different classes. The first is CVAG 4423, which is transportation infrastructure. And this is a required senior level class. And what I did is I used Road Resource and I divided the class into groups, and each group explored a single maintenance treatment and a single rehabilitation treatment on the entire RDOT network. Now, this is of course not recommended, but it does explore the difference between maintenance and rehabilitation. And I'll get into more of that later on. Now, most of the students who took CVEG 4423, which is a required class that I teach in the fall, then went ahead and took CVEG 4863, which is sustainability in civil engineering. And this is a senior level tech elective. So it's not required, but it's one of the options that students can use for one of their tech electives. And what we did is we moved beyond this basic project, which looked at one treatment on the entire network, and we compared conventional to optimized treatments on the RDOT network. Now, of course, all good studies have assumptions, and I'm just going to briefly mention these assumptions here. First of all the treatment costs were national average costs, so there are no regional adjustments. So if you go to roadresource.org, they have default both costs and default life extensions. And I'm fully aware that costs vary around the country, and I'm fully aware that the life extension of treatments varies based on a whole host of factors. But for these projects, just to introduce these topics to the students, we use the default costs and life extensions. We also did not use any salvage values. So there's a lot of literature out there that talks about at the end of the pavement life, that pavement has some sort of value associated with it. And that value can be a benefit to looking at one treatment or another. And so because I did not use any salvage values, depending on where they were kind of chopped off, how long they were supposed to last, and then where the analysis period ended, this did penalize some treatments more than others. And then finally, this was an academic exercise, so I do not recommend that one treatment should be applied on an entire network. But I do think it's a great exercise, especially to introduce people to the topics of pavement preservation, pavement maintenance, and pavement rehabilitation, because it shows trends in extreme scenarios. So it's very academic, but it really does allow students to start understanding these concepts from a high level. And I used RDOT, Arkansas Department of Transportation data. So thank you, RDOT, for providing this to me. And they provided the 2018 RDOT network. And I think that the data they shared with me actually had 6 or 7 highway types. But for the sake of simplicity, I broke that down into just 3 different highway types. So I looked at freeways, multi-lane highways, and 2-lane highways. And you can see a lot of us are very well aware of, we have a lot of 2-lane highways in the state of Arkansas and relatively few freeways. And of course, the traffic is flipped on that. The vast majority of traffic is on our freeways, and the lowest volume roads are our 2-lane highways. So I did take multiple categories of highway types and break it down into those 3. And then I also used the 2018 budget for just the maintenance and rehabilitation, which was about $237 million. And for the sake of this presentation, if you go to roadresource.org, there's actually 5 total calculators. Actually, I'm sorry, there are 6 total calculators. And for the first part of this presentation, we're just going to focus on 2 of those calculators. We're going to focus on the life cycle cost and the remaining service life. So the remaining service life is one of my favorite new units. I think most people are familiar with the life cycle cost. You just don't look at the initial cost of something. You look at the cost over the lifespan. And I used a 50-year analysis period for this project. But the remaining service life is something that not everyone is familiar with. So the way that I think of remaining service life is I first think about the units. And the units of remaining service life are lane, mile, years. So let's pretend we have 1 lane mile of road. If we don't do anything to that road, so if we don't put any preservation treatment on there, we don't put any maintenance treatment, we don't do any rehabilitation on it, after 1 year, we experience a 1 lane mile year loss. Now we can compare that to if we have that same lane mile and we put a treatment on that, let's say, lasts 4 years. After 1 year, you have a 3 lane mile year gain. And this is a very powerful concept because it takes a look at an entire network, which we know is very complicated, but it gives us an idea, is our network heading in the right direction? Are we heading in a positive lane mile years? Or is our network heading in the wrong direction? Is it heading in a negative lane mile year? Because in theory, we want our network to improve over time, so we want to have positive lane mile years for our remaining service life. And now what we did for my first class, the transportation infrastructure, is we put one treatment on the entire network, which again, I don't recommend. And you can see the treatments are listed here. We looked at a 50-year analysis design, and the treatments that you see here are the maintenance treatments. And so you can see in the lower left-hand corner, we have a rejuvenating fog seal. So according to roadresource.org, a rejuvenating fog seal is placed every 3 years on a pavement. So if you place a rejuvenating fog seal across the entire network, RDOT's entire highway network, every 3 years over a 50-year period, it costs about $6 billion. And then you can see you kind of move up in cost as you get into crack seal and fog seal. So those are all just asphalt emulsion based treatments. But then you get up into chip seal, slurry seal, and scrub seal. So those are combination of asphalt emulsion and fine aggregate or aggregate. Then you get into some more robust mixture treatments, including microsurfacing, cape seals, and a double lift microsurfacing. And then finally, the most expensive are the hot mix base, the bonded wearing courses, the thin lift HMA, and the ultra thin lift HMA. The really nice thing about this is each student group has one of these maintenance treatments. And so when I show this slide during class, they can see where their treatment is, their maintenance treatment. And then they can kind of see where the other treatments line up in relation to their maintenance treatments. So they have one maintenance treatment, and the costs are shown there. And then you also have the rehabilitation treatments. And you can see this is pretty interesting because the most expensive maintenance treatment, the ultra thin lift HMA layer, is just under $25 billion over a 50-year period. Are we okay, Zahid? I'm going to assume we're okay. Zahid's at the podium, but I figure he'll wave at me if something's not okay.
Yeah, you are good. I'm just muting some folks like that. Yeah, you go
Perfect.
ahead.
Sorry,
please.
Zahid. I just wanted to make sure. Now, getting back to the slide, you can see there's a very interesting trend here. If you look at the maintenance treatments, the ultra thin lift HMA is just under $25 billion. If you place it, I think it's every 11 years on every lane mile of Arkansas's network. But then if you look at CIR, which is cold in place recycling with 2 chip seals, that's right about where that ultra thin lift HMA is. So in a way, you can kind of extend the graph for maintenance, and it just kind of keeps on going up in a relatively linear fashion as you go from cold in place recycling to minor mill and fills, which is 1.5 inches, to cold in place recycling with 1.5 inches of hot mix or 38.1 millimeters, to a hot in place recycling, to major mill and fills, full depth reclamation, and then full depth remove and replace. So again, all the student groups have one maintenance treatment, and all the student groups have one rehabilitation treatment, and they can see what are the similarities and differences between maintenance and rehabilitation, and how does that look in a life cycle cost. And what we call optimized treatments generally cost less than conventional treatments. So we have a lot of mill and fill here in the state of Arkansas, but I would say that there may be some opportunities to explore some of these other optimized treatments, such as cold in place recycling. And I'm very happy to report that RDOT has been placing some hot in place recycling on our roads. So it's very exciting to see us start to explore some of these different treatments, because I'm not trying to recommend any one treatment. I'm just saying there's a lot of tools in the toolbox, and how can we use all of these together in order to maintain a very high quality network. Now, this is the remaining service life. So if you remember, the remaining service life has your lane mile years. And if you remember, in general, you want to have a positive lane mile year, because that means over time your network is improving. And these are all the same maintenance treatments. Now they're going from the upper left-hand corner to the lower right-hand corner, but it's essentially the same order. And as you get to more intensive treatments, going from just the asphalt emulsion all the way down to the hot mix, your lane mile year decreases. And this means that there's a lot of treatments out there other than just an ultra thin bonded wearing course or a thin lift HMA There's a lot of different surface treatments out there that we can be exploring that actually have a higher benefit to our pavement network over time. Now, what gets really interesting is we take a look at this graph, the maintenance graph, and then compare it to the rehabilitation graph. Because you can see here immediately, very similar to the life cycle cost, the rehabilitation treatments kind of pick up where the maintenance treatments left off, and only CIR, cold in place recycling with 2 chip seals and a minor mill and fill, have a positive lane mile years for rehabilitation. All of the other rehabilitation treatments actually have a negative lane mile years. So I'm lucky, I'm an academic. I realize that this is an extremely complex situation. And we have roads that are in poor condition that require rehabilitation. We don't want to put a rejuvenating fog seal on a road with a lot of fatigue cracking and a lot of rutting. That's just throwing our money away. We need to do some rehabilitation. But if we kind of take a step back and just say, hey, how can we start taking care of roads that are in good condition with these maintenance treatments? Take care of that surface, because if we can start taking care of some of those roads, then we'll need to do less of that rehabilitation. And there's a big discussion out there about the worst first strategy versus more the preservation strategy. And the worst first is talking about how you're always only taking care of roads in bad condition. But that's a cycle you'll never get out of, because you can see here with RDOT's network and RDOT's budget, if you're always doing worst first, you're always going to have a negative lane mile years. You're never going to get it out of that cycle. So how can we start balancing that? So a couple big takeaways that I want the students to get from this exercise is that maintenance provides a higher level of remaining service life than rehabilitation, and all but 2 rehabilitation treatments have negative lane mile years. So again, this is very high level. This is just trying to introduce the students between the difference between maintenance and rehabilitation. I tend to think of maintenance as looking at just the surface of the road. Rehabilitation looks at the structure of the road. So getting these concepts out there to the students, that there are different ways that we can take care of our networks, I think is very important. Now, again, I do not recommend that we place one treatment on RDOT's entire network. That is not good practice. And so for the students who choose to take CVEG 4863, the Sustainability in Civil Engineering, they get to explore some optimized treatments. And so what we do here is we kind of take a look at the treatments that RDOT has traditionally used. And as I mentioned, they're starting to move into some more of these, what I call optimal treatments, which I'm very excited about. And so start kind of comparing what RDOT uses mostly about these other treatments that are available, and see what happens when comparing those 2 sets of treatments. Now, we also introduced a new term, existing service life, and this is the age of pavement in terms of condition. So kind of file that back in your head, ESL. I'll go over what the definition of that is in a minute. We also defined T-Pres. This is the time to achieve true pavement preservation. And again, I'll define that. And here's the verbal definition, and we'll go over some examples so you can see it in action. But my definition of true pavement preservation is all of your pavements are either in a PCI A or PCI B. Now, I realize RDOT now uses the MAP 21 criteria with rutting and cracking, but the roadresource.org uses PCI A through F, so it's a very helpful tool to incorporate. But my definition of true pavement preservations is all your pavements are on PCI A or B. So in my mind, that means that there's no rutting and no cracking, or very, very light rutting or cracking. And the key here is that you have 0 lane mile years gained or lost per year. And to me, this is very important. It's my humble opinion, and I have a lot of opinions that I'm more than happy to share with people, but it's my humble opinion that our industry has not done a very good job of really clearly defining preservation, maintenance, and rehabilitation. And if you've noticed, I've even been kind of using preservation and maintenance kind of interchangeably in this presentation. Something that I've thought a lot about, and trust me, I think about this a lot, is I think of preservation more as a mindset, more of keeping a network in good condition. And in order to preserve a network, you need to apply treatments. So you need to do something to the road, whether it's a rejuvenating fog seal, a chip seal, an overlay, whatever it is, you need to do something to that road. So you want to preserve your network. So that's kind of a global concept, but then you can apply maintenance treatments, which have to do with the surface, or you can apply rehabilitation treatments, which have to do with the structure. So I'm really excited about this concept of true pavement preservation, because basically it's talking about what kind of condition do we want our network to be in? And we want it to be in a very good or good condition and not getting any worse or better. That's the ideal scenario. And we call that true pavement preservation. And so I had, I think in the previous class, I had like 70 or 80 students. This is a smaller class, which is nice because you can really dig into some of the details, because this is a very complicated discussion. But this is a smaller class of 14, and we divided them into groups to explore different groupings of optimized treatments. So before I get into those groupings, let's talk about existing service life. I promised that we would define that, and I don't want to disappoint. So existing service life, what this does is it represents the amount of time pavements have been in service. So let's walk through an example of this. So let's just take a PCI A. We multiply the age of each PCI by the length in the network. So if we have a PCI of A, you can roughly estimate that your year range will be between 0 and 12. And this, we can then use an average age of 6 years. And this is a debate. We can say it's between 0 and 10. We can say it's between 0 and 14. We can say it's not consistent. But for the sake of this, we're just assuming it's between 0 and 12, and we're using an average of 6 years. So then what we do is we take each highway type, so our freeways, we say how many lane miles are in a PCI A condition, and then we multiply that by 6, and we get lane mile years, and those are the freeways that are in good condition. And so here's a table that you can see this broken down. So we have our PCI grade in that left-hand column. We have our year range that we assumed, and again, that's an assumption. We have the average of that year range. And what we did is we took that average and multiplied it by the length, and then we get the ESL. So 6 times 1166 is 6996. And then if you go all the way down to PCI F, there's only 111. Well, in 2018, there were 111 lane miles of freeway in poor condition, or PCI F. You take that 111, you multiply by 20, you get 2,220. But you can see there, those are the freeway ECLs for each PCI grade. And you can perform a similar exercise for multi-lane highways and 2-lane highways. And I don't have the lengths written here, but you have the ESLs written here. And everyone is very familiar with this. We have a very chronic problem that by far the highest number of lane miles are 2-lane highways. But if you take a look at this existing service life, by far the highest number of lane miles in PCI, D, and F are on those 2-lane roads. And this is tough, because those are the low volume roads, but those low volume roads tend to be in worse condition than the higher value roads. But anyway, all that being aside, this is the existing service life. Now let's take a look at T-Pres. So T-Pres is that existing service life, the ESL, and we divided that by the remaining service life. And this is a simplified assumption, but is essentially what we're saying is that if we're able to take care of roads in good condition, and then divide it by how much life roads have in good condition, we can get some sort of unit of time, and we define that as T-Pres. And so this T-Pres, what it represents is the time to reach what we call true pavement preservation. And again, that's where the entire network is in a PCI A or B, and you have the 0 net lane mile years of RSL. So now that we've defined ESL and T-Pres, we can explore what did we do in class. So what we did is we looked at what I called the conventional treatments. So Arkansas uses a lot of chip seals. It uses a lot of minor mill and fills, which is 1.5 inches, a milling, and 1.5 inches overlay. And it uses a lot of full depth remove and replace. And these are great treatments. I'm not saying that they're not in any ways, but RDOT does use quite a few of these treatments. What we then did is we utilized the remaining service life calculator on roadresource.org. We treated the same percentage of PCI D and F roads. At the same time, we treated 100% of the PCI A roads. And this is absolutely critical. We took care of the roads that are in good condition. We treated 100% of those. So by treating 100% of those, and then treating the same percentage of PCI D and F, we then maximized the remaining surface life within RDOT's budget. Then what we did is we calculated the T-Pres for each highway segment. We did ensure that the PCI, D, and F can be treated within the T-Pres. So that was our one little gatekeeper to make sure that these kind of lists of assumptions and how we went through the process were valid. But this is somewhat of a simplistic exercise, but it showed some interesting trends. But then what happens is over time, you're fixing the D and F roads, and those are getting put up into A roads. But if you're treating the A roads, you're going to consistently have those stay as A roads, and the D and Fs will decrease. And the B and Cs will slowly fall down to D and Fs, but that number will decrease as you continue to take care of those D and Fs. If you're treating 100% of the A roads, in theory, those won't slip down. So you're kind of moving everything up into that A and B category. Now, what we had to do then is we had to shift a remaining budget to the next highway segment. So we started with freeways first, then we went to multi-lane highways, and then we went to two-lane highways. And I'll go through all these. But this is just a very broad overview of what we did in order to try and see, can we get RDOT's network using our existing budget into an A and B condition, the entire network. Now, I do want to recognize that RDOT does not do a whole lot of treating PCI-A roads. And I don't blame RDOT at all, because there's a lot of roads that need work. But I would like us to start thinking about taking care of our roads in good condition. And you'll see why here in the upcoming slides. So this is using our current treatments. If we put chip seals on PCI A and B roads, minor mill and fills on PCI D and C and D roads, and then a fold up remove and replace. What we did is we allocated the budget due to how much traffic was on each one of these roads. And so what we did is we have our original budget. So this is a function weighted on how many lane miles there are and how much traffic there is. So that kind of gives a little more weight to the two-lane roads because they don't have much traffic, but it does ensure that the freeways, which have much more traffic, are being taken care of. And I want to reiterate here that it's absolutely critical that we're putting this chip seal on PCI A and B roads because this is a key part of pavement preservation. Now, what we did then is we weighted the budget, as I mentioned, to traffic, and we used vehicle miles traveled. And so these original budget numbers here are weighted based on the VMT, the vehicle miles traveled. And so you can see the vast majority of money is going to freeways and freeways in good condition. And that is because we want to keep those roads in good condition and they have a lot of vehicles. But using this method, weighting it by vehicle miles traveled, we're also making sure we are spending enough money on multi-lane roads and two-lane roads. And so you can see the original budget here listed for multi-lane highways and two-lane roads. Now, I mentioned briefly, excuse me, I'm going to take a sip of water here. Now, we mentioned briefly that I started adjusting the budgets, and I'll show how I went through that adjustment. But these adjustments are shown here in these second columns. So basically what we did is once we got the freeways into A and B condition, we shifted money down to multi-lane highways. We got the multi-lane highways in good condition, then we shifted down to two-lane highways. So that's what this adjusted budget is. And that was done after True Pavement Preservation, or T-Pres, was reached. So let's go through an example of how we did that. So according to our analysis, if we would spend $94 million a year on our freeways, treating our PCI A, B, C, D, and F roads, it would take 2.21s to bring all of our C, D, and F roads up into A and B condition. Now, if we spend $94 million a year for 2.2 years, we will reach T-Pres. And that means that all of our pavement in freeways is in A or B condition. And if you remember, once you get to T-Pres, you simply want to have 0 lane miles gained or lost. We're not looking to increase or decrease, we just have 0. So we can reduce our budget to keep it in A and B, and that reduction is $9 million approximately. And then what we can do is we can shift that money down that we just saved on our freeways to multi-lane highways. So if we go through this adjusted budget, we start with our $94 million for freeways. Once we get to T-Pres, after 2.2 years, that means our entire network's in A and B condition for freeways, and it's not getting better or worse. We only need to spend $8.9 million. So we take the 94 million, we subtract 8.9, and then we add the multi-lane budget, which is 48 million, and we get 134 million. Now, this is very powerful because with RDOT's existing budget and weighting by vehicle miles traveled, we can get to T-Pres in 2.21 years for freeways, and not adjusting the budget, we can get to 13.8 years in multi-lane highways. So just chugging it through the system, keeping the roads that are in good condition, and moving the roads in poor condition up into good condition. It would take 13.8 years to do that on our multi-lane highways, spending $48.8 million a year. But once we shift the money from freeways, it goes from 13.8 years to about 4 years. So using that $134 million, we can do it much more quickly. And then keeping the multi-lane highways in good condition only costs $11 million. And we can take those savings then and shift it down to 2-lane highways. Now, you may be asking, why am I talking about this original versus adjusted if it just speeds it up? Well, with the conventional treatments, it's interesting because with the current RDOT budget, if we weight it with the vehicle miles traveled, you'll never reach T-Pres with the original budget. It's not possible. Your roads are getting in poor condition too quickly. However, if you shift the money from multi-lane highways, you can see the budget goes from 93.5 million to almost 217 million, and then you can get there. It'll take 86 years, but you can get there. And the amazing thing is, if you do these sequences, if you take care of the roads in good condition, if you slowly bring the roads in poor condition up to good condition, and you continue taking care of roads in good condition, within 92 years, RDOT's entire network can be in a PCI A or B condition, and the budget will be about $90 million, which means that we save about $147 million. Now, this is obviously idealized. There's loads of assumptions. I guarantee you things will happen where you need to do more rehabilitation, but this does give you a direction and an idea of what could possibly happen. So the takeaway from here is that T-Pres is 92 years using these conventional treatments, the chip seals, the mill and fill, and the full depth remove and replace. Now, the previous class project, I advocated there are more tools in the toolbox. So what if we use some more of these tools in a toolbox? So for freeways, what if we use this suite of treatments? Rejuvenating fog seals, microsurfacing, mill and fill, CIR, and full depth remove and replace. For multi-lane highways, what if we use rejuvenating fog seals, scrub seals, CIR in 2 different forms, and full depth reclamation? So CIR stands for cold in place recycling, FDR is full depth reclamation, and then the R&R is full depth remove and replace. And then for 2-lane highways, we break it down into rejuvenating fog seals, chip seals, the 2 types of CIR with 2 chip seals placed on top and with hot mix asphalt, and then full depth reclamation with 4 inches of hot mix asphalt. Now, we could have a very robust discussion as to whether or not these individual treatments are appropriate for each highway type and for each pavement condition, but we harvested data from our sustainability class that looked at a whole bunch of treatments. We harvested data, and we feel, based on engineering judgment and that data harvesting, that these give us the best bang for our buck. And what we can do is we can go through the entire exercise that we just went through for the conventional treatments with these, what I call optimized treatments. So this is a very similar table, but we're using different treatments. So you can see now the T-Pres for freeways is 2.5 years. For multi-lane highways, it's 10.4 years and 3.4 years using the adjusted budget. The 2-lane highway, you still can't get there without adjusting the budget, but when you adjust the budget, you get 40 years, which means that for the entire network with the optimal treatments to get to a condition of A and B with neither positive nor negative lane mile years gained or lost, it would take only 46 years and it would cost $81 million. So we'd save approximately 155. So what we did is we went from 92 years to 46 years using more treatments. So again, please, I have no problem with chip seals. I have no problem with mill infills. I have no problem with full depth remove and replace. Those are great treatments. But let's talk about opening that toolbox up more and using some of these other treatments and see what can happen with our network. And this is just one example. Now, there's another calculator on roadresource.org. So we looked at the life cycle cost calculator. We looked at the remaining surface life calculator. A third calculator on there is the environmental calculator. And this used 3 publications to get this data. You can see one's from BASF, one's from NCPP, the National Center for Pavement Preservation, and one's from COLAS. So this is where they got the numbers for in order to develop this calculator. And what they looked at is a whole bunch of different factors. They looked at hauling emissions. They looked at availability of wrap. They looked at different climate impacts, treatment application procedure, all these different things. They looked at a whole host of different factors. And this calculator is also on roadresource.org, and you can work through these treatments. And the reason that we looked at this calculator is because I defined sustainability in 3 pillars. One is economic, which was the life cycle cost. One is environmental, which is this environmental impact calculator, and the other is social. So for the sustainability class, it's very nice to have this environmental exercise incorporated. And what happens is you can plug these treatments in and you get reduced greenhouse gas emissions versus a major mill infill. And you can see there's a significant amount of reduced greenhouse gas emissions when you just take care of the pavement surface. So starting with the rejuvenating fog seals, the crack seals, and the regular fog seals, going to microsurfacing and slurry seals, to chip seals, scrub seals, and cape seals, you can see all of these surface treatments have significant reductions in greenhouse gas emissions compared to a major mill infill. And then even the hot mix treatments, the ultra thin lift, the bonded wearing courses, the thin lift, they have significant greenhouse gas reductions. So that means a reduction of emissions, just taking care of that surface, applying maintenance, and not applying that rehabilitation. And I presented this slide at a couple conferences, and some people say that these numbers are high. And I think that there is a range of numbers, and there are so many factors that go into here. But something that we can all agree on is that these surface treatments, just taking care of that pavement surface, you have fewer greenhouse gas emissions than if you have to start taking care of the structure, the rehabilitation, which is where the major mill and fill comes in. So in conclusion, these 2 classroom projects, what they did is they showed that maintenance provided a higher remaining surface life than rehabilitation. All rehabilitation treatments had negative lane mile years, which means that if we're doing that worst first, we're just in that cycle of roads and our networking in a worse condition. We defined true pavement preservation as your entire pavement network being in the PCI A or B with your remaining service life of 0 lane mile years. If we just use the conventional treatments, the chip seals, the mill and fill, and the remove and replace, we could, in theory, reach true pavement preservation in 92 years. Now, that's a tough sell to politicians because most politicians' lifespan is not 92 years. But I think it's very important to show that it can be done if we treat the roads that are in good condition, we keep them in good condition. But then if we use optimized treatments, there's more tools in the toolbox, we can reduce that. And again, these are idealistic numbers. There's a ton of variables that could go into. I cannot sit here and say, you know, I guarantee it will take 92 years if we do this. But I think this exercise is useful because it shows us the direction we can go in. And whether it's 92 years or 86 years or 110 years, to me, that's kind of a moot point. I think the point is that if we better allocate our money, if we treat our roads in good condition, and if we expand the tools in the toolbox, we can move toward having a network in better condition. So that's the main takeaway here. So that's all I got. I'd be happy to take any questions. And if you'd like, you can feel free to send me an email as well. And I think we have a couple minutes. So I'm happy to take as many questions as necessary. But thank you very much for your time and attention. So I assume like everyone's yelling questions at the same time. So it's just mass pandemonium, right, Zahid?
In the room, we do not have any question, but there might be some questions from audience at Zoom. If you have any question, please unmute yourself and ask the question. This is a good class, Andrew. Thank you. I appreciate.
Yeah, if there's no questions, but if you have any comments or if you have any follow-up, there's my email. Please email me. I'd be more than happy to continue the discussion. But Zahid, thank you for inviting me, and thank you for your hard work with this conference. You've done a tremendous job year after year, so thank you.
All right. Thank you, Andrew. And looks like, it's excellent presentation. I see a lot of the prospect is very high to save lots of money. If we do the right type of preservation and maintenance work. So let us give a round of applause to Andrew, and thank you again.
Thank you guys. I appreciate it. Take care.
Okay, so I'm going to do this. All right. The next speaker in this technical session is one of our own, Dr. Ashraf El-Said. Dr. El-Said received his PhD and master's degree in civil engineering from the University of Alabama in 1995 and 1991. I'm sorry, I copied it from somewhere. It should be reverse. 1991 and 1995 probably, respectively. He received his BS in civil engineering from Cairo University, Egypt in 1982. He serves as an associate professor in civil engineering at Arkansas State University. He has 7 years of experience in highway and airport construction area. He has 33 years of experience in the geotechnical engineering area, including several projects in the Middle East. He has 11 publications and more than 70 presentations in the areas of transportation and geotechnical engineering. His areas of research interest include geotechnical and earthquake engineering, pile dynamics, and soil stabilization. He is a licensed PE in 16 states. Let me make you the host, co-host, Dr. El-Said, so you can share your presentation. And let me also stop my sharing. So Dr. El-Said, you should be able to present your screen, share your screen now. So please help me welcome Dr. Ashraf El-Said.
Right, can you guys see my screen?
Not yet. We see blue screen. Yeah, there you go. It's good now.
All right. Okay, so Zahid, thank you for your presentation, and we're gonna change direction a little bit and talk about construction issues and construction matters. And for those of you who's familiar with highway transportation construction or bridge construction, usually it goes through a process we call design, bid, build. So RDOT will either design a bridge in-house or ask one of its consultants to design, and then that bridge is going to go out for bid, and there's going to be a contractor winning that bid, and he will construct the bridge. So the contractor comes to play late in the picture after the design is completed and everything is ready to go. The CMGC project delivery is an alternative delivery that will require legislative action. So what we're going to be talking about today, we're going to define what's a CMGC. We're going to give you a background about a project that led to the one we're going to be talking about, project objectives, a little bit about the subsurface exploration, and then the design and construction and challenges. And at the end, we're going to talk about the lessons learned, the benefit of the system, and we'll leave a minute or so for your questions. So what is CMGC? It stands for Construction Manager General Contractor. As I said, a minute ago, usually in the design bid build system, the contractor comes to play later in the game. Everything is designed. And usually when there are construction matters or issues or problems or challenges come up, then you will have a square table. What I mean by that is the DOT and the representative on one side, the contractor and his representative on the other side, and it usually arguments that lead to delays and overruns, sometimes litigations on extreme cases. The CMGC system actually brings the contractor to the picture way in the early design, of the early part of the design. So we as engineers, we know all about how we design bridges, highways, and such, but the contractors know better about how to build them. So when you bring a contractor in the picture early in the process, you can actually get pricing, information about alternatives, and more importantly, constructability. So this project here was sponsored by Tennessee Department of Transportation. And as you'll see, why we're bringing a contractor in the process that early to form basically a partnership. So the table goes from square to round, and everybody will be on the same team and have the same goals. We're trying to mitigate risk, improve constructability, and reduce construction time, because for these projects, time is more important than money. You know the saying, we always can make money, but we cannot make time. So to the cost to the user, and in terms of construction schedule and delays, those are a whole lot more important than what the project actually costs in terms of construction budget. So the project we're going to be talking about is in this area here, that's part of Memphis. And if we zoom in, you will see that interchange here. This here is Poplar Avenue, and Poplar Avenue is by far the most traveled route within the city proper, and it goes over Interstate I-240 here. There is, west is to the left here, so there is a westbound Poplar, eastbound Poplar, and we have these 4 bridges here. 1, 2, these are east and westbound Poplar, and you will have a bridge over the railroad here. That's CN. That's I'm sorry. We're gonna talk about the railroad bridge here in a little bit, and then you have Park Avenue down here, which is a bridge that's not going to be replaced, but it's going to be improved. So a little bit of background to this project. There was an earlier widening project of I-240 that took place a few years before that CMGC project. And it's going to extend from Walnut Grove Road to all the way to north of Highway 385. It's a little bit over 2 miles. And the idea was to widen I-240 to 4 lanes each direction. And that will require building 15 retaining walls. And to enable the widening, you have to excavate the bridge abutments. So in order for you to maintain the stability of the abutment and widen the road, you have to use a system to retain the soil, and the system planned for that one was a combination of soil nails and anchor walls. And for all these 5 projects, eastbound, the West Poplar Avenue, the Shady Grove Road over 240, Park Avenue, and then Norfolk Southern Railroad over I-240. So this is a picture of that widening project in process that took place from 2011 to about 2014. So to widen the interstate under the bridges, you have to use that soil nail, which is a top-down construction technique. You start excavating at the top, You put nails and anchors, you excavate more, you put nails and anchors all the way till you complete the excavation at the interstate level. So based on the record, there are paths actually is supposed to be supporting the abutments, and they are supposed to be extending a sufficient distance below the tow elevation, which is the interstate level. So design was completed, and first bridge was westbound Poplar, and the contractor was ready to excavate, and then he saw this. So if you ignore all the safety violations that this guy on the photo is doing, he was looking at this point here, which turns out to be the tip of the driven path. These paths were driven in the mid-60s. So the equipment for driving paths were limited, and they basically got to a refusal point. They thought that they have capacity, and the paths stopped. Bridge has been working fine for 50 years. There was no concern, but now we're going to excavate around it. So I can tell you that day when that excavation took place and the tip of the path was exposed, there was quite a bit of people nervous on that construction site. So we had to come up with a solution real quick. And the solution to that was actually to build another abutment in front of the existing abutment. So if it happens that we compromise the existing paths because they are short during construction, we will have another abutment that will support the bridge. So you will see here the old abutment, which has the two paths, one straight and one better. They are short. Now we're driving deeper paths in front of that auxiliary abutment, which basically is supposed to take all the load and assume that the old abutment doesn't carry anything. There was a system of anchors and nails, and then we're going to build a facing for that retaining wall. So that started taking place right away after that system was approved. You see here we're cutting through the existing bridge, and we're torching the steel, and then we're going to have a hole ready for each pile driven through these holes. And this here shows the finished product. This is a new auxiliary abutment supported by H piles, and here are the system of anchors and nails. After that was put in place, we had to shotcrete it. So now the system is basically stable. Shotcrete is just for preventing any erosion from the face of the soil. And then after that, we had completed the soil nail anchor construction, and then we put a facing in it. So this is how it looked at the beginning of the CMGC project. That facing here doesn't carry anything. It doesn't have any structural value, just for the looks. But because of this condition here, we could not widen the interstate under the other bridges. Another challenge was that you will see here, we have a retaining wall that's supposed to be constructed here, and then you have this TVA tower. Was supposed to be a soil anchor wall in front of that TVA tower, and TVA said, you are not going to put anchor under our tower. So we could not widen the interstate at that location. So there was quite a bit of work left after the initial widening job was completed. Basically, we widened the interstate, we came under the bridges and went from 4 lanes to 3 lanes. So it's like you haven't done anything. So the CMGC project had this objective here. We need to complete the widening of I-240. We're going to have to improve 4 deficient bridges, either by replacement or rehabilitation. And then we need to improve the horizontal and vertical clearances. Some of these bridges didn't have enough clearance per AASHTO requirements. And then in the meantime, we're going to have to maintain the traffic over the existing bridges, meaning that we're going to have to close the interstate only over weekends for a specific number of times. So the idea was for people to drive on the old bridge on Friday evening and then drive on the new bridge first thing Monday. So over the weekend, you're supposed to demolish a bridge, put the new bridge in place and open traffic on it. So that required a system called accelerated bridge construction, ABC. That's not usually the cheapest method of construction, but it allows for a faster construction. Again, for the highway user, time here is more important than money. So that was the team that TDOT put together. Benish was the lead, project lead and designer. Gresham Smith out of Nashville handled the ITS and other constructability issues. Barge design will require, responsible for the roadway structures. Geotechnology did the geotechnical exploration, and Kuwait Infrastructure South was a contractor. And I'm sure quite a few of us here in Arkansas are familiar with Kuwait. They are handling all the I-30 widening in Little Rock, and they have built a bunch of other huge projects in Arkansas. So here is a little bit of synopsis about the bridges we are dealing with here. The red arrows show these bends are going to be taken out, and the green ones shows the abutments are going to stay in place. So that here, westbound Poplar is about 295 feet, and you have a little bit over 16 feet of vertical clearance, which means it was okay in terms of vertical clearance. This is the eastbound Poplar, the second bridge. Again, this abutment here and this bend are supposed to be taken out, that bend also. So we're going to change that bridge from a 4-span bridge only to 2-span. We're going to build new abutments, and we're going to improve the center span, which you see right here. That's Park Avenue, which is a bridge you're going to stay in place, but it's just going to get rehabilitated. And the big deal was changing or replacing that Norfolk Southern Railroad bridge over the interstate. And I don't know if there is anybody from the railroad on this call, but I have to admit, working with the railroad is a little bit challenging because they have their means and methods, and it's their way or the highway. TDOT used to say they own that bridge, but Norfolk Southern tell them what to do with it. That bridge also has a little bit of deficiency in vertical clearance. You see 15.6, that's less than 16 feet. And it's actually a 6-span bridge. So the plan for Norfolk Southern, that we're going to keep these supports here, and we're going to take that one out. And from that point, we started our geotechnical exploration. So you would see in this plan here some borings and some other test points over that project site. And if you look at these photos here, you see quite a bit of overhead power lines. When you try to drill, and I don't know if Paul Tinsley is still on the call, but if you try to drill with a conventional drill rig here, and you have to raise a boom 30 or 40 feet in the air, then you have to stay a minimum distance away from these lines for safety of the workers. And that did not allow, these existing overhead lines did not allow for that. So we had to rely more on cone penetration testing because of the low overhead clearance. Basically, the top requirement is the top of that rig here, and you're pushing a rod into the ground to the depth you need. So there is no overhead issue, overhead utility issue when you do CPT. So subsurface conditions, there was a hard sand layer, a very dense sand layer, about 30, 35 feet. That was the layer that where the piles rested on for the abutments, and the middle bends for the bridge was actually shallow, supported on shallow foundations. And the shallow foundations were on the top of that dense sand. So that was good back then in the 60s. Now with the change in seismic codes, that support had to be on pause because Memphis is influenced by the geomagnetic seismic zone, which is probably the major seismic zone in the United States. You zoom a little bit on that, you will see some of the information. We have about 15 feet of silt and then a little bit of clay, and then you see the very dense sand down here. Typical output of the cone penetration testing, you will see, you have a normalized cone, cone resistance, you have the friction ratio, you will have the pool water pressure, and from that you can come up with what we call soil behavioral type. So it tells you that soil will behave like sand or behave like clay. It does not say it is sand or clay, it says it behaves like sand or behaves like clay. Because of where the project is and the influence of the new moderate seismic zone, bridges needed a site-specific ground motion response analysis, which was done, and you will see the published H2 design spectra here in dotted red and the site-specific in solid blue. So for bridges with natural period, up to half a second or so, you will see you get quite a bit of reduction in the design seismic accelerations. Very long bridges are going to get slight increase actually. And that's typical of what you see in the Memphis and West Tennessee area. So geotechnical recommendations were just typical. You have slope stability analysis, you have global stability analysis for walls, and then you will have typical recommendations for micropause. These are parameters we require for micropause, and we're going to talk about that here in a minute. Typical soil, characteristics, unit weight, on-drain shear strength, effective angle of internal friction, and for lateral load, you will have some information here too, as in terms of soil modulus and E50. These are required parameters when you run lateral load analysis on deep foundations. Par recommendations in terms of driven edge paths, you will see non-factor nominal loads with depth and numbers for in terms of total compression or uplift resistance. Again, nominal values. So construction started, it was supposed to start in January 1st, 2018. It actually kicked in about a couple of weeks earlier and finished about 5 days ahead of schedule. And those 5 days ahead of schedule means a few $100,000 of in terms of saving to the users, again, in terms of time, that time shortening resulted in. So general idea about the project, you have the blue bridges were going to be replaced and the yellow bridge is going to be rehabilitated. So you will see here, because of the low overhead clearance that we're supposed to work with and the very tiny and very busy construction area that does not allow you to close lanes or things of that nature, you have to innovate a little bit. So micropaths were used extensively here. You see over 26,000 miles, 26,000 feet of linear feet for micropaths. You will see the retaining walls, those maroon here are showing retaining walls widening under the bridges. And you will see the edge paths that were driven when the overhead clearance allowed at the locations. And then you will see different types of retaining walls. So we had freestanding soldier pipe piles. You have soldier piles with dead man anchors. You have soldier piles with grounded anchors. All that is dictated by how much room you have to work with. And then when you had a chance, we built conventional cast in place retaining walls. So nail walls under this bridge. And these following few slides will show you actually what the plan was for these bridges. So this bridge here, Park Avenue, it had 4 supports that were supposed to be improved. And then we're gonna build the brand new abutments here. So these abutments needed soil nails, and then this photo here shows the location for retaining wall 13, which is this line, this red line here. And you can tell here is the TVA tower, here is another tower, and then you have the bridge you have to work under. And one of these bridges, the Park Avenue, which is on the top, that will stay in place while the bridge here for Norfolk Southern will be replaced. So we had to use a little bit of innovation here. We ended up with 7 different types of retaining walls. Each one will fit a specific stretch when we can actually, we're limited only to 1 or 2 items. So around the TVA towers, we could not put any anchor, so it has to be a soldier pile freestanding or cast in place. While under the bridges, we have to use soil nails with tiebacks, different types of tiebacks. So this here is retaining wall 13 in construction. You see here the soldier pile in place. And then the face of the soldier pile, dead man anchor wall. And here is the sheet pile, which we used for as a dead man. These are photos during construction. And you'll see the difference, the distance between the existing bridge and where you are putting the wall was pretty tiny, very narrow area. So there was no room for error when the construction is going on. This was the real main challenge for that project, Norfolk Southern Bridge, because you cannot just take the bridge out of service. The railroad has to maintain its operation. So the idea was to actually build a temporary bridge for the railroad to operate while you are replacing the existing bridge. So this here showing the 2 lines on the existing bridge. And then we're going to build what we call a shoe fly. A shoe fly means it's a temporary bridge you can use for operation till you complete construction. And then we're going to slide the 2 active lines to the shoe fly, the temporary bridge. And then we're going to take out the existing bridge. We're going to build the new bridge in. And then we're going to slide the superstructure on the shoe fly to where the new supports are. So we build 2 support systems and 1 superstructure that we actually pushed from 1 support to another. And I will show you a video of that here in a little bit. That was basically the bulk of the project. So this here, it's photos taken during the operation. You will see the train is running on the existing bridge while the shoe fly, the temporary bridge, in construction. Here is the existing bridge, here is the new bridge and the new supports. So these are the new supports, and this is the center line of the shoe fly, and then this is the permanent alignment that used to be before construction and is supposed to be after construction. East and west bound poplar bridges. So we have here 6 supports, 5 spans. And what we are going to do is we build a 2-span bridge, new abutments on each side. And we have a new support here. And then we're going to build these bridge panels in what we call a bridge form. And then we truck them in and put them in place. And that will happen only in 1 weekend. You demolish the existing bridge and you put the new bridge in 1 weekend. So this here was the existing abutment. What we did to it is this here. So we excavated the abutment and we put soil nails and anchors in there. And then we put micropods to support the new support. We build the new support. We backfill between it and the new abutments. We remove the bridge, remove the support, the old support, and then we put the bridge panels, bridge deck panels, and we finish completion of the abutments And that all again takes over 1 weekend. So these are photos taken during construction. This crew here was putting micropiles in, and you will see the overhead room availability. You could not drive piles under this bridge here. That's why micropiles were used. Some of these micropiles equipment can actually go through a regular building. Some of them are pretty small. So these here are the micropiles ready to build the new cap to encase them all. And you will see here, that's the existing, the old support, and this is the new support. Some more photos taken during construction. The backfill, which require using crushed stone and geogrid. And this is how the middle bends were handled. So this is the existing footing, which was great supported, no piles. So we closed a half a lane from each side so we can move traffic outwards. And then we excavated around it. And then we put new supports, which are micropiles. And then we encased the whole thing in concrete. So now you have a brand new support that actually meets today's AASHTO standards. This is a photo taken during construction. So you see the old support while the new support is being formed. And that was driving piles in this apartment. These piles were driven during to support that apartments, and a couple of more photos during construction. Now, we mentioned a few minutes ago that we are building the bridge panels, and then we're going to trunk them in. So this here shows where what we call the bridge farm. These are where the panels are going to be constructed, and then we're going to put them in self-propelled modular transport SPMT vehicles, and we move them 2 miles down the road during the weekend when the interstate is closed. So this is an aerial photo taking for that panel of the bridge during construction. Reinforcement in there, pouring concrete, and now early in the weekend, that panel was put on that self-propelled modular transport SPMT and ready to be moved 2 miles up the road to where they're supposed to be placed. So this photo here was taken during the weekend. No traffic on the interstate, and these SPMTs, they're pretty slow. Usually there is a guy operating or operate them with a remote control, and they move them about, they move about 2 miles an hour or something like that, and you can understand why. So we close that bridge on 9 p.m. Friday night, and demolition takes place into Saturday morning. Completely remove the bridge and site cleanup. And after the demolition, you can see all the equipment now, in rest. That was a photo taken by a drone during that weekend. I cannot tell you how many drones were flying around that site, owned by the state, the surveyors, private people. It was just a scene. And then you see these 2 cranes here. These were German made, and during the operation, these are about 600-ton crane capacity. The Germans were actually monitoring the performance of these cranes in terms of tire pressure and lift capacity in real time, and making adjustment as they see fit. So the cranes were in operation while the manufacturers were monitoring the operation in Germany. Now you see that they actually placed the panels, and then you have the joints here being finished. Completely finished joint. And then we pave it, and we're ready to open that bridge on Monday morning about 6 a.m. So that's here a schematic of what actually went in to use the existing support. So the existing support is on the upper left and the new support on the upper right. And these are just schematic showing the steel and how it end up as a final product. Park Avenue Piers, same thing. You see the new support, and you see a guy standing in there just to get a sense for how big that support is. And for building that support, we had to put new macropiles around it, and then we have to encase the old foundations with the new macropiles in one big mat. And that was just before pouring concrete. These are photos to construction progress. There were also driven piles in that job. So I'm gonna, just for the sake of time, I'm gonna skip that part. I can actually provide this presentation in a PDF if somebody is interested in how the challenge in driving piles using different pile driving formula. And we proved to TDOT that the engineering use formula should be put to rest and never been used. And they start using other formula, one like the modified gate, which is listed in the H2LRD bridge design manual, or the Washington State DOT, which is a much superior formula. So just for the sake of time, I'm gonna skip that, and I'm gonna go to this here, which is the weekend of the first bridge replacement, taken down to about 2 minutes video. And I'm gonna have to apologize for the music. I was not, I did not pick the music. Actually, I suggested to TDOT to use like background music by the Bee Gees, and they didn't listen to me. Okay, the next one is actually for the one of the two first slide of the Norfolk Southern Bridge. We said that we build the superstructure, put it on the temporary support, and then we're gonna push it from the temporary support to the permanent support. And this video shows that. Again, I apologize for the music. one here shows the last slide. I guess you got the idea of, that's a weekend when you can actually make that move. It was perfect, success, and all comes down to how capable the contractor is. So just to wrap it up about the benefit of that system and the lesson learned from general perspective, the contractor got under contract during the design, helped the design team. There was some innovation in terms of the support systems and the type of materials used. And by the time he was ready for construction, he had a full understanding of what's at stake, and he helped with the constructability part during the design process. Identified risks before construction and helped mitigate them. And that system allowed also for early procurement, which is a major cost saving. ABC is not the cheapest option, but is in a heavily traveled urban environment. Sometimes it is the only option. From designer perspective, implemented the accelerated bridge design, results in less than 1 year of lane closures, only about, I think, 6 weekends for interstate closures. And then we had a very tight workspace we had to work with, which required innovation. Utility is always a big deal. So that system allowed for minimized utility relocation, which is always a good thing to do. And then issues were identified, dealt with in a timely manner. The contractor was aware of all the plan from the get-go, and he helped develop it, so there was no surprise. And in terms of the railroad, that minimized impact on railroad operation, and which is always a challenge with these bridges in urban environment. From the owner's perspective, we had a great approach to fit the history of that project, very high ADT. So completing that in the minimized time that we had was a major success. And then all the partners were around the table. There was no argument. Everybody is on the same team. And we had a game plan for every challenge that we knew about ahead of time. Traffic conditions were basically, there was a minimum traffic impact only during the weekends when we had interstate closure, but besides that, traffic was flowing very fluently during the construction. From the contractor perspective, there was quite a bit of experience that we got from the contractor and he got from the design team, dealing with these basically key stockholders here in Norfolk Southern Railroad and Memphis Light Gas and Water. We had a key in the project, but without the CMG system, that project would not be even close to the success it had. Also, another attribute of that basically the continuity from the design phase to the construction phase, the same team handled both, and that usually results in much smoother process. From Memphian, the people who live in Memphian perspective, the impact on their lives were very little during construction, but they asked why you have to build 2 bridges. The answer was, in order to maintain the TDOT operation, there was no way around it. So we had to build 1 superstructure, but two supports, and just to maintain the operation by the railroad. So that completes my presentation. I think we have a couple of minutes for questions if anybody has any.
Looks like we have a question here in the room.
Okay.
For the Mark Simachek, I'm in research at RDOT. I was wondering, for the slide of the railroad bridge, what method did they use for the lateral force to slide the bridge?
Well, it was all about reducing friction. So there was a lot of detergent and pumps, horizontal pumps that actually put against the support and again, and from one end, and against the bridge superstructure from another end. And there were people spraying detergent over the steel all the time just to reduce friction. So it was a simple system of pumps that you set them horizontally and you operate them at the same time, so they push the bridge superstructure the same distance every time you pump them out. Kiewit has done that in the past, and that helped to a great deal because they were, they had experience with that system, and it just worked out to perfection. But after that was done, there was a ton of, detergent bottles everywhere on the interstate that somebody had to clean them up.
Thank you.
Okay, looks like there is something, Dr. El Sayed, are you able to read the chat box, or do you want?
I'm sorry?
There
Oh,
is- yes, chat
let
box,
me get
yeah.
out of that. Okay.
I don't know if
let's
it is a
see.
question. Oh, okay, yeah, it is, yeah, Mohammed Abdul Mazid is saying that, thank you, Dr. El Sayed. I have a question. Is CM-ZC more effective than EPC in the construction process from the contractor's perspective? Could you comment on that?
Well, the CMGC, it's not for any contractor. It's for contractors with specific qualities that they have to have the capability, and they have to have at least minimum background and about design process. Kiewit is a huge contractor. They have offices just all over the place, and they operate on many continents, and they have a huge design group. So they were no foreigner to design process. So most of the contractors not familiar with it. They're concerned that it's basically cut them out of work. But from what I'm seeing, it's a major improvement over conventional, design bid build process. So, but it's not for every contractor. So I believe DOTs now are going through training programs to contractors about the CMGC system, which requires a little legislative action. So your state legislators have to authorize that. And that was done, I think, a couple of years ago in Arkansas, and RDOT is going through its first CMGC, or already gone through a couple of CMGC projects. They are designed in-house.
Thank you, Dr. El Sayed. Are there any other questions? Looks like none. Thank you so much, Dr. El Sayed, for this very nice presentation. I enjoyed the videos. Musics were like, it woke some people up as well. But I love those videos. Yeah.
Okay.
Thank you for putting all these things together in such a short notice and presenting your work so many people, I guess, like involved.
Thank you,
and-
Zaid, for all that you do.
Yeah, all right, so let's give you a round of applause. Okay, next thing on our agenda is we are going to take a short break. So that is a short break, and we are going to come back at now it is 2:15. So we'll come back at 2:30 here. So for our the third session of the technical presentation. So we have 2 more presentation after we come back from break. So let's take 15 minutes break. Thank you.
Hey, Mark, how's it going?
It's fine, David. Saw there's a message here where you called this morning.
Yes, as it turns out, I needed a structural number, the D value on some funded project that I had previously requested the SN values for the flexible pavement.
Okay.
So I was just gonna call and talk to either you or Michael. At the time, I was thinking.
So we already responded. Forward that to Alan. He can get that information to you.
Sure, we'll get that memo out to you.
Okay, that'll work.
It hasn't already gone out, I'll get it out to you.
Or just send us an
Hello,
email.
good
and we'll find you
afternoon.
this list.
We are
Either way is
back
fine.
for our technical presentation session number
No problem. Thank
3.
Bye.
And it looks like we still have maybe, yeah, I think it is 2:30 already. So we will go ahead and get started. But we have the presenter already. He is ready sharing his screen, but let me introduce the speaker, since the speaker already shared his screen. I'm going to... Okay, folks, if you are not the speaker, please mute your microphone so we do not have background noise. All right, Mr. Jim Musselman, he is a senior engineer for the National Center for Asphalt Technology, in short NCAT, where he is currently involved in various research projects and training activities. Prior to joining NCAT, Jim spent 30 years with the Florida Department of Transportation, where he was the state bituminous materials engineer. Jim was also an asphalt performance manager for CRH Americas Materials for 3 years. He has worked in the area of asphalt materials and construction for over 36 years. Jim has both a bachelor's and master's degree in civil engineering from the University of Florida, and also a registered professional engineer in the state of Florida. Please help me welcome Mr. Jim Musselman for his presentation.
Hey, well, thank you very much. And can you hear me okay?
Yes, perfect. Yeah, we can hear you. Also, we can see your screen very well.
Excellent.
So please go ahead.
Excellent. Well, again, my name is Jim Musselman. I'm a senior engineer at NCAT at Auburn University. And my disclaimer that I'm going to have is I had the flu last week and it was pretty bad. So I don't know how good my voice is going to be. So bear with me if I choke up a little bit. Plus, we're talking about asphalt, so I always get choked up over asphalt. Such a good topic. So today we're going to talk about making, basically quality pavements when we use wrap material. And wrap material, if you're not familiar, is reclaimed asphalt pavement. So typically, if you mill off the top surface of an asphalt roadway, you take that material, haul it back to the asphalt plant, and we basically recycle it into a new asphalt mixture, and we call it wrap. So if you're not an asphalt person, that's what it is. So I'll talk to you a little bit about some of the facts and figures about how much asphalt we use and how much wrap material we use nationally and regionally. A little bit about wrap materials evaluation, management, and then some of the things that occur during mix design, production, and construction. I got a lot of data from the National Asphalt Pavement Association, NAPA. They publish every year, they do a survey of all the asphalt contractors that are members on the amount of wrap material that they use, warm mix, and I actually think recycled shingles as well. I think this work is funded by the Federal Highway Administration, and every year they publish this report, and it's on their website. So if you're ever looking for information on how much wrap material is used or warm mix, it's contained here. And that's where I've gotten most of these facts and figures. So anyway, typically in the United States, there's about 87 million tons of RAP that are used in new pavements annually. So that's quite a bit. And over 93% of the material that we take off an old pavement, we end up using it again. And if you translated that to actual materials savings in terms of how much would we pay, think about what RAP material is. It's aggregate that's coated with asphalt binder. Now the asphalt binder is a little bit harder and it's oxidized, but it's still asphalt binder and it's still aggregate. So if you looked at those material savings for raw materials, it'd be about $3 billion annually. And that kind of conserves over 24 million barrels of asphalt binder and 82 million tons of aggregate. And that's significant, not just in the availability of more aggregate, but it also saves us the energy costs and the greenhouse gas emissions associated with producing, processing, and transporting aggregate and binder. And it also saves some good landfill space. If you were working in the asphalt industry, maybe back in the 60s and early 70s, you know, if they ever milled up an asphalt pavement, which was kind of rare, they would actually haul the RAP material off to a landfill. So it's something that, you know, it's a wasted resource. These are the average RAP contents by state, and I'll give you a second to kind of adjust to the color coding. The darker green means the average is over 30%. So, you know, my home state is Florida. Okay, and let's see if I can do the laser pointer. Here's Florida, and their average for all mixes statewide is 34%. In Arkansas, it's 14%. So that's the biggest swing you'll see between the two. It's kind of a unique thing. Florida does not have a lot of natural native aggregates, so a lot of it gets imported. There's quarries down in South Florida, but a lot of it gets imported from other places, either Alabama, Georgia, or it even comes in by ships from Nova Scotia, Canada. So there is always a shortage of materials in Florida, but you can see how different states use it. The average RAP content in the United States is about 21%. Again, the average in Arkansas is 14%, so a little bit lower there. If you were looking in terms of what sector of the construction industry, where are we putting the RAP, you can see that you know, the dashed green line at the top, that's commercial and residential work, and so that's averaging about 24%. The purple line is just the overall average that I just gave you, which is, I said 21%, I think it's actually 21.4. But the little dotted blue line is the DOT usage, and then other agencies, and those would be local agencies, cities and counties, and they're both hovering right around 20%. If you look at some of the other neighboring states down here in the south central portion of the United States, you can see the average is, you know, bumping around 20%, and 20% is a fairly standard number kind of nationally. Obviously, if the national average is 21%. So the benefits of using RAP material is obviously it saves money, as we've kind of covered. It allows milling without generating a waste. It can potentially speed up construction, eliminates the waste material. I think we've already said that twice. And it's a sustainable practice, and it reduces greenhouse gas emissions. Now that's a significant thing because the National Asphalt Pavement Association has stated a goal of by the year, I think it's by 2050, that the asphalt industry will have like basically a net zero carbon emissions in the production and construction of asphalt. So that's a big deal. They recently published this report on their website. And so for every ton of RAP material that we use in new asphalt mixtures, it reduces basically the amount of carbon emissions by about 27 kilograms. And if you did it nationally, if we increase the RAP content 1%, it would result in a reduction of about 0.14 million metric tons of CO2. So that's 140,000, I think, metric tons in avoided emission. And that's pretty significant. So that's something, again, the asphalt industry is working towards. So the next thing when we're dealing with RAP, let's just talk about some of the basics about some of the materials evaluation that we should be doing to make sure that, you know, that we're using the right materials, we're designing the mix properly. So typically in an asphalt mix design, these are the primary materials and secondary materials. We've got aggregate, asphalt binder, which is the black stuff, and then whatever recycled material, which would be RAP or possibly RAS. RAS is recycled asphalt shingles. The use of RAS material kind of peaked maybe about 10 years ago, and it's kind of decreasing a little bit. I'm not going to get into RAS today. Some of the secondary materials that are used in asphalt mixes include polymers, ground tire rubber, warm mix additives, rejuvenators, anti-strip additives. There's a lot of things, hydrated lime, things like that. So there's some real good information in a couple publications. This is NCHRP report 752, which coincidentally was done by NCAT. However, I didn't work for them then. It was Randy West was the PI. However, I was on the panel that oversaw this research. So they really had some really outstanding recommendations in that. And also NAPA has published a document called Best Practices for RAP and RAS Management. And both of those are good documents to use, particularly for any contractors that may be listening. So these are the recommended from the work that NCAT did. It was probably about 10 years ago. You can see this is what some of the recommended practices, let's say as we're milling up an asphalt pavement and we're taking that RAP material and we're stockpiling it back at the asphalt plant. As we build that stockpile, what we need to be doing is typically about 1 per 1,000 tons, determining the binder content, making sure we get at least 10. We're going to recover the aggregate and determine the size of the material, determine the gradation, recover the aggregate, determine the bulk specific gravity. That's an important thing when we do a volumetric mix design, and then actually recover the binder and do some PG grading. And this gives you sort of the general frequency that they had recommended and the number of tests that should be done per stockpile. So again, some generally good information. In addition, in the right-hand column, it gives you some recommendations on if you've got maybe RAP material that may be excessively variable. So for example, if you run your 10 stockpiles on binder content and you calculate your standard deviation, and if it's over 0.5, that may tell you that you've got more variability than what would be typical in that RAP stockpile. So again, just some good information to use for both contracting people as well as agency folks. This is sort of the same thing done a little bit more schematically. We obtain the samples from the RAP stockpile. We're going to get at least 10 or more samples in the left-hand part of the flow chart. Maybe I'll take this to kind of flow it down a little bit. We'll do the ignition method or a solvent extraction. And from that, we can determine the binder content as well as the gradation. And then we'll combine those recovered aggregate samples and determine the bulk specific gravity and any other aggregate tests we may need to run, fine aggregate angularity, that sort of thing. And then we can determine the averages and the standard deviation. Then we'll get at least one sample, we'll extract and recover the binder, determine the true grade of the RAP binder, and then basically determine what would be the appropriate RAP content in this mixture based on not only the binder content and the gradation and the variability there, but also the characteristics of the recovered binder. So this is just an example. This is a front end loader using a front end loader building a miniature stockpile and getting samples of those, getting those samples again as they're building that stockpile. So when we characterize some of the RAP aggregate, and one of the things RAP aggregate, you know, it needs to be good quality and it's got to be consistent. You know, that's true for any aggregate that we use. I know a number of states maybe have some restrictions on the amount of RAP based on the amount of carbonate that may be in the aggregate, things like that. So sometimes it's related to the frictional characteristics of the RAP material. For example, Florida has limitations on the amount of RAP in the surface mainly because there's some sources in Florida that it's not polish resistant material, so it would tend to polish under traffic. So these are some of the typical properties that would be evaluated, maybe prior to the mix design, but probably the ones in red down at the bottom are the most important, the specific gravity and the absorption, because that's a big part of the mixture volumetrics, and we'll talk about that in just a minute. So again, we'll determine, as we're doing this materials evaluation, we're going to determine the RAP, bulk specific gravity, which is abbreviated G with a subscript SB. We'll determine the RAP gradation, the RAP binder content. And with that, we'll look at the averages as well as the variability. And then we'll characterize the RAP binder. We'll recover the RAP binder as well as the virgin binder. One of the things about RAP bulk specific gravity is if there are errors in how it's determined, because it's not quite as simple as taking a sample from a stockpile and running T84 or T85. And so there's different ways to determine the specific gravity, which we'll talk about. But you can develop an error in your VMA. VMA stands for voids in the mineral aggregate, and we'll kind of go through what that means. But VMA errors will typically result in lower than calculated effective binder contents. So again, in this graph, if we are using, say, 20% RAP, and we think that we've got a GSB of 2.700, but it's really 2.660, it's off by 0.04, you could see it's affected the VMA by about 2 or 3 tenths. Maybe it's not all that significant, but again, with a higher RAP content mix, some agencies are up in the 30 or 40% range. That could make a big difference. So just something to be aware of. Again, it's, and we'll talk a little bit as what's the best way to determine the RAP bulk specific gravity. Again, because it's used to calculate, as you can see in that formula, the VMA of the asphalt mixture. And so why is VMA important? Basically VMA kind of controls the volume of effective binder. And what effective binder is, in real simple terms, is that's the amount of asphalt binder that doesn't get absorbed into the aggregate. Okay, and that's what provides the best durability, the cracking resistance. So in simple terms, if you want a mix that's crack resistant, you try to add more asphalt binder to it. Okay, so that's just something to kind of keep in the back of your mind. So in terms of determining the RAP bulk specific gravity, there's really kind of 3 ways to do it. You can recover the RAP aggregate using the ignition method, and then conduct T84 and T85, which that's probably the best way to do it. Or you can recover the RAP aggregate using a solvent extraction. And then the third way is that you can estimate the bulk specific gravity based on some other measured properties, the maximum measured specific gravity, the binder content in the mix, and again, an assumed asphalt binder absorption. And then you kind of do some back calculations to determine the GSB. Again, the first 2 methods typically provide similar GSB values, and they're probably definitely the best. The third method relies on, you got to be able to accurately estimate how much of that asphalt was absorbed into the RAP material, which is kind of like dissecting a sneeze. It's really hard to tell. You can't look at an aggregate, a RAP particle, and say, oh, I know how much there's 3/10 absorbed into the RAP. So it's kind of a little bit challenging. So anyway, the first 2 methods are typically the best. RAP gradations, again, as we talked about, so you'll sample and test. You'll get the average gradation, the binder content, the standard deviation, and then you'll use that data, the mix designer will, to determine the potential impact on the overall mix gradation at various RAP contents. And so, for example, if let's say that the standard deviation on the number 8 sieve was 3.8%, and you're using 20% RAP, that's only about 0.75% variability that you're adding to the number 8 sieve, and it's only increasing your standard deviation by a little bit. However, if you increase the amount of RAP material, then certainly it's going to have a bigger effect. Same thing with virgin aggregate. So again, one thing about RAP gradation, sometimes it's difficult to tell just by looking at what the standard deviation is what's the, is this, you might look at the blue chart over here and you'd say, hey, on the number, the number 200 sieve, the 0.075 millimeter sieve, there's only a 1% standard deviation. That's pretty good. But if you look at the coefficient of variation, that kind of gives you maybe a little bit bigger picture of what's going on. That's the standard deviation divided by the average, and it's a percentage. So coefficients of variation less than 20 in the aggregate world are generally considered good. I might use the word okay. I don't know if we ever get good. And so, for example, on the P200, we have a standard deviation of 1%, an average of 5.2. And if you calculate the coefficient of variation, you're up to about 20%, which you're kind of borderline. So it could be a little bit problematic. RAP binder characterization, again, that's the important thing about RAP. Again, the aggregate doesn't age, but the asphalt binder does. It oxidizes with time, and it gets harder and more brittle. So what we do is we sample the RAP material, we extract the binder, we recover the asphalt binder, and then we'll do a continuous grade, well, typically like we would on a virgin binder material. So there's a number of things that can affect the binder characteristics on the RAP material. It could be what was the original binder to begin with, where was the project located, how old was the project, maybe it got milled up 5 years ago and it's been sitting in a stockpile. So all those things can have a big difference. For example, if you're in South Texas, you've got maybe a little bit more sunlight than you do maybe up in Montana. And so as a result, you might have more oxidation just from, the sunlight than you would get, from up in North Montana. So again, these are some examples that came from that NCHRP report from different agencies that actually tested their RAP material. So you can see in Alabama, they looked at 36 stockpiles. And what they saw was that their typical high critical temperature when they graded the binder was a 91.7. Their low critical temperature was a negative 12.5. Now, most of these binders probably went out as something around a 64 minus 22. So, I mean, or probably back in the day, they might have been old enough that these might have been an AC 30 or an AC 20. Which again, probably would grade out as somewhere around a 64 minus 22. You can see my home state, Florida, it was about a 95 minus 16. Indiana was a 90 minus 11, and Wisconsin had an 82 minus 21. So you can kind of see the range, but typically the high critical temperature is normally at least up in the mid to upper 80s. Again, can be a little bit higher depending on where you are. Now, one thing we talked about RAS earlier, if you were to grade RAS material, that number, the high critical temperature might be something like 120 or 130, so significantly stiffer. So the other thing you'll do is during kind of prior to the mix design process is on the PG binder that the contractor is going to be using in their mix design. Let's say they're going to use a 64 minus 22. They'd want to get from the binder supplier what the actual true grade on that binder is. Okay, and we'll use this information in just a minute. So here's a 64 minus 22. This is a certification on the material. This is a 58 minus 28. And its true grade was the 61.2 minus 30.6. So you can see the actual true grades. And again, those should be available, readily available from the binder supplier. So if you had no idea what type of binder to select, like if you go back 20 years to the, when the US was adopting the SuperPay binder spec, you might look at a graph or a chart like this, which kind of gives you an idea. Now, this is the desired low pavement temperature that you're going to have at a 98% reliability. So down here in the Southeast, you can see there's a lot of, like, Florida's red, should be a minus 10. And like the southern part of Arkansas would be like a minus 16. The northern part would be a minus 22. What you've kind of seen in the Southeast is pretty much everyone uses a minus 22. for the low temperature, and probably and same thing on the high temperature, you would have a grade there. You could actually pinpoint it. So on this LTPP bind, which I failed to mention, which is software that's provided basically by the FHWA, you can click on a certain location and it'll tell you that, like, for example, in Little Rock, you ought to be using technically a 64 minus 16, and I think the Arkansas DOT specifies something like a 64 minus 22 as their base asphalt binder, okay? And then there's certain grade bumping that we're not going to go into today, but that's basically, so we know a little bit. So what we want is our binder to be, say, a 64 minus 22. So now that we know the binder characteristics of the wrap, and we know what the characteristics are of the virgin binder, if you use an AASHTO method, you can actually determine how much wrap you can put in that mix. So it's a simple formula. It's like, this is the temperature, the critical temperature of the blend. So if we wanted a minus 22 and we know the critical temperature of the virgin binder and the critical temperature of the wrap, we can plug all that in. It's a simple little formula. So for example, here we wanted a minus 22 low critical temperature. The binder that we're going to use, our virgin binder, is going to be a PG 58 minus 28, okay? And we know from the binder supplier that that minus 28 is actually a minus 28.7. And we've tested our wrap material and it's a negative 11.1. So we plug these numbers in, and mathematically, that tells us that, hey, we could use up to 38% wrap with those binder characteristics, and we still would hopefully not be any warmer than a minus 22 degrees. So that's kind of how that process works. There are some other things that are looked at as well, and I'm not going to go into too much detail as this, but some of the low temperature testing that occurs on an asphalt binder, they measure kind of different properties. One is the stiffness. You'll get a stiffness critical temperature. There'll be a relaxation critical temperature. And the difference between those two is called delta TC. And so that's something that generally when you utilize a virgin binder, you want to use a virgin binder with the highest, more positive delta TC available. So if you had a delta TC of -6, that isn't always real good. A maximum delta TC, or minimum, I guess I should say, we want it warmer than -5 degrees C. And so -5 degrees C was being considered by AASHTO for mixes containing RAS material, and I think they may have dropped that. So there's an increasing interest in using rejuvenators. That's another type of asphalt binder that are used. You know, if you think about wrap material, there's a couple things you want to do. Is so you want to basically reduce the viscosity because it's stiff, but also the chemical composition of that wrap binder has kind of changed. And so rejuvenators have the capability of enhancing the quality of that binder. And then there's another factor when you deal with rejuvenators: how well do you get it dispersed and diffused into the old wrap material? You know, if you spray it on, it may kind of coat the outside, but maybe it doesn't mix in real well. So there's different ways to apply rejuvenators. It can be pre-blended into the virgin binder, which is probably the best way. You can pre-treat the wrap by spraying it on maybe the wrap conveyor as it's going into the drum. And then you kind of have to look at binder quality versus the wrap quality when you're doing that. And one thing to note is it's an emerging technology that I don't know if any state has actually nailed down the use of rejuvenators, but it's something that is certainly being looked at. And particularly as we're looking to increase the use of recycled materials, personally, I think that rejuvenators is going to be the kind of the answer to the problem on how do we take an old cracked up asphalt pavement and kind of make it new again. So that's just something, an emerging technology. As far as materials management goes with wrap material, you know, wrap stockpiling and handling, it's somewhat similar to the way we handle aggregate. It's that generally you want to follow the stockpiling best practices. You want to minimize any sort of segregation or contamination, things like that. And you also want to minimize the amount of moisture. Moisture is a big deal at an asphalt plant. It's more, if you more water you get in the aggregate, the more you have to dry off. And if you don't have an accurate moisture content on your aggregate, it's going to affect your binder content in the mix, and it costs money. There's a lot of bad things associated with moisture. So again, there's some recommendations of what can be done to eliminate moisture. You could see, I think this is an asphalt plant, I believe down in the Tampa, Florida area. These aren't necessarily wrap piles, but you can see that they do have a paved area where the stockpiles are placed. And you can see it's actually graded, so the water will drain off the wrap stockpiles. And just a good way to save energy and also, help the aggregate not be so wet. There's one of the things you don't think of much, but you can actually have segregation problems with wrap material, just like you can other types of aggregate. Now here's a shot. I don't think you can hear the sound, which is not that classy music that comes from Memphis, Tennessee, I got to tell you. Anyway, this is just the sound of kind of like the conveyor up in the aggregate. You can see the coarser particles that are kind of rolling down to the side of it. Okay. So anyway, if you take the coarser particles, you would get a completely different size. So the little pile on the left would roughly be about a 1/2 inch size particle by number 4 or 1/4 inch. And if you measured the binder content, it'd be about 3.5%. On the right-hand side, it would be maybe the 1/4 inch material all the way down to dust size material, and it'd have a much higher binder content. So you could see something like this, as you're feeding it into the wrap bin, you're getting both. So if you get a slug of the fine stuff going in, it's going to change the binder content in your mix. When the coarse stuff goes in, you're going to get a slug of coarse aggregate going through the drum. So those can affect the binder content. So if you're using 20% wrap in a mix, and you've got part of it at 7.5%, because it's segregated, at 7.5% AC, it's really contributing 1.5% AC to the total mix. But then you suddenly, it drops down to 3.5% because you're in the coarse part now. The difference is 0.8%. So that's in the total binder content of the mix. That's going to allow some volumetrics. If it reduces the binder content that much, it's going to be a problem getting density on the roadway, et cetera. So anyway, so it's just important on how we handle and stockpile wrap material. Wrap can come from different sources. Probably the most common is milling operation, but it also can be full depth removal, where they're tearing down a convenience store and they tear up the parking lot and they bring in big chunks, and the contractor basically crushes them up and uses them in an asphalt mix, or it can even be wasted plant material. So those are the three sources. Millings are typically the way projects are milled, or particularly on state highways or state funded projects. They're typically fairly consistent because normally projects limits are generally set about where the old project limits were. So it's typically the same mix as being milled up, or same type of mix. And it's going to have similar gradations, binder content, aggregate properties, and binder properties. And so, for example, on millings, you really may only need to sample and test the stockpiles, and you can almost use it as is. I know, for example, where I'm from, contractors would routinely screen the millings just to make sure that they were more uniform in size. And again, if the maximum aggregate size is too large, you can scalp it or screen it. You can fractionate, which we'll talk about in a minute, or you can process it by crushing it down to whatever size you're looking for. So again, the other thing is, if you have stockpiled or unprocessed wrap that comes from various sources, and you'll see that a lot at an asphalt plant. And that might be the waste pile for the contractor, or where they bring in chunked asphalt, and you can see there's a lot of sources, and they typically require some type of processing. So that would be crushing and screening, and in some instances, fractionating. And one thing you got to be careful of is that you don't let any, base material or lime rock material or something like that contaminate the wrap pile. There's a lot of words on this slide. The bottom line is the very first bullet. is when you crush wrap, it's going to generate more fines. So if you do that, ideally, if you're going to crush and screen, you ought to screen it first and then crush it, because otherwise you're going to be crushing those fines and generating even more fines. Typically for a mix designer, the amount of -200 or the amount of fines in a mix is what challenges them the most in terms of being able to meet the volumetric requirements. You know, you heard me talk earlier a little bit about fractionated wrap, and it's something that's a little bit more elaborate than just crushing and screening, but typically it comes from a multiple source stockpile where they'll crush it, that'll go through a wrap bin, they'll screen it into different sizes, and typically 2 or more sizes. And that gives the producer a little bit more opportunity to make changes to the mix. And again, normally that's done for mixes that have higher wrap contents. And they've got a lot of wrap material, and they also have a lot of space at the plant, you know, because you've got multiple stockpiles of wrap. A lot of asphalt plants, particularly in urban areas, they don't have that type of footprint. Or if you've got problems with the mix design requirement, if you think about how we use virgin aggregate, you know, we don't put it all in, it's not all one size. It's typically a number 8 stone, a 78 stone screening. So they're separated into sizes. This is essentially doing kind of the same thing. This isn't something though the agency should mandate. It really needs, you don't nearly need to develop a method spec. This is something that should be the contractor's choice to do, because it's a pretty heavy investment in the equipment to do this. And if they can meet the requirements without fractionating, they ought to be allowed to do that. So talking a little bit, excuse me, about the mix design process. One thing about asphalt, if you're not familiar with it, you know, it's a gigantic pendulum of performance. And when I first started, I was a co-op when I was at the University of Florida back in 1985, and I worked for the asphalt lab with the Florida DOT. And back then it was all about rutting problems. And Florida made a number of changes through the years, including adopting super pave, which tended to dry up their mixes a little bit. And the rutting problem is completely gone. But guess what now, you know, and all the states had a rutting problem back in the mid 80s. Well, now they all have cracking problems. So now, you know, states are doing things to try to get more asphalt back into the mix design. So again, you get it too wet, you get good durability, good crack resistance, but poor rutting resistance. You get it too dry, you get excellent rutting resistance, but poor cracking resistance. So these are some key parts of the mix design process. You got to make sure you characterize the materials right, just like we discussed earlier. Use the design, use the actual materials, use the appropriate binder you're going to use. Consider the plant's capability to produce the mix as it's designed. If you've got an old wore out asphalt plant, it's probably not a good idea to design it with 40% wrap. And then consider doing some type of performance testing. We're not going to get into the balanced mix design, but performance test is typically some type of rutting test or and then some type of cracking test. So if you did the balanced mix design process, you might use the Hamburg wheel tracking test on the left to determine the binder content with respect to rutting, and then maybe the ideal CT test, which is shown here on the right, which will give you the right cracking test and cracking resistance for the right binder content. But again, when you look at different available rutting tests, there's a bunch of them. There's I do say it, the asphalt pavement analyzer is there, but they've got, you know, things that are done with the AMPT. And so you can go very, very complicated on this. And then the cracking tests are there's even more of them. Right now, I would say that the ideal CT test and the IFIT are kind of two of the most common. I think the Texas overlay test is also very common, particularly in the south central part of the US. And again, they're all good tests, and they just need to be kind of calibrated with real world scenarios just to relate them to actual performance. And then the third part of that would be any type of moisture damage tests. And a lot of states use the tensile strength ratio, which is AASHTO T283. Some use the Hamburg test, and some still use the old boil test where you put the mixture in water and you boil it. As far as production goes, there's some basic practices you use when you're using wrap material. You want to make sure that the wrap feed is properly calibrated and properly maintained. You want to make sure the wrap stockpiles are uniform, they're not contaminated, there's not that type of segregation that we showed earlier. You want to look at the wrap binder content, because again, variations in that binder content can affect the variations in binder content in the mix as well as the volumetrics. Monitor the moisture content in the wrap, and also make sure, keep an eye on the loading operation. Loaders have the capability to do the most good or the most harm when you're actually producing an asphalt mix. Talk a little bit about construction, and I had to stick a Gator flag in there, just even though it's a rough year for football. So I don't know anybody really wants to talk about football unless you're, from Alabama or I don't know, Tennessee, I guess. So anyway, always any project, you got to have quality construction. And so we've all heard this, that you can have, a great mix's field performance can be screwed up by poor construction techniques. Likewise, you can take a marginal mix and get actually pretty good performance out of it by getting, good mat and joint density and getting good smoothness. And again, one of the things too is for the folks on the roadway that the plant, it's important that they talk back and forth. Folks at the plant, if they know that, hey, this is a very stiff wrap material we're using, that handwork is going to be difficult, that needs to be communicated to the paving crews so it's not a surprise. Anyway, so some of the conclusions that we've got: that use of wrap, it's a sustainable practice that can reduce the production of greenhouse gases. That's a good thing. Wrap's got a proven record of good performance when it's properly designed and produced. And then the use of recycled materials are going to keep asphalt at a competitive price and provide value to the agencies as well as the traveling public. And we always use best management practices to make sure that we're putting good quality mixes out there. So if I'm looking right, I think I'm 3 minutes ahead of time, and so I've got a minute or so for questions. Are there any questions? Oh, I'm seeing a couple in the chat log, so bear with me. Nope, I don't see any. Well, that's all I have for you. There you go.
Can you hear us?
No, I can't, and I've lost the screen too, so I can't see you either. Let me turn up my volume. That might help.
Hello?
Okay, go ahead.
All right, David Henning from the Construction Division with RDOT. We are meeting, Materials Division and Construction Division will be meeting with the Arkansas Asphalt Paving Association later this month. We are proposing some required quality control tests, much like you've shown in your presentation, in order to allow higher wrap usage in Arkansas. Industry has also requested, right now we have special provision that does not allow the use of wrap in any of our PG 76 -22 mixes. Industry has also requested that, but we want to establish and make sure everybody has good quality control procedures when handling wrap, which we do not have right now with all of our producers.
Yeah, and I think that's a key part. And certainly if they can get a handle on the gradation and the binder content, and at least maybe characterize, I don't think the contractor is going to characterize the binder, but they can send it to a private testing lab. As far as using the PG 76 -22, I know that, a lot of states allow maybe up to like 20% wrap when they're using a polymer. And I can understand the rationale is that, hey, you're paying a little bit premium for that polymer modified binder. You don't really want to dilute it with the wrap binder, but it was something I know that Florida back probably 10, 15 years ago when Florida first started using polymers, we didn't allow any wrap, and we were like, no, we don't want it. But now they allow, I think, so I retired 5-6 years ago, and but I think they now allow up to, I believe it's 25% wrap if there's polymer. Now, the flip side of that is HYMA binders. If you ever use high polymer, that was one that most states do not allow any wrap. But I would say that states allow from 10 to 20% when they're using polymer.
Okay, thank you. Are there
Okay.
any question, any comments? Was there something on the comment box, in the chat box? How to calculate, it is a specific gravity of aggregates, apparent specific gravity, I guess, of wrap.
Yeah, it's a little, I can't really explain it over Zoom for two reasons. One, first off, I'm not smart enough to explain it. But it's basically what you do is you run the Rice test on the wrap material, and then you determine the binder content of the wrap material. And I think from those two things, you can calculate the effective specific gravity. There's a standard formula on how to calculate the effective specific gravity based on the GMM and the binder content. And then you can kind of work backwards and calculate the bulk specific gravity, but you have to make an assumption for the percent binder absorbed term. So again, that's the better way to do it on wrap material is to actually just extract it and test it.
Okay, thank you for that clarification. Yeah. All right. Are there any other question from the audience in Zoom? Oh, what is that question? Is this the new chat? Does the balance mix approach limit the amount of wrap without a specification limits?
Yeah, and that's I think Dr. Hussain, I think that's a great question, because I think, if you going back to like the 60s, everybody was using Marshall mixed design, then we all switched to the super paved system. And now the push is to move more towards balanced mixed design, where you're running performance tests for both rutting and cracking. And really that's we're dealing with a northern state on the use of wrap right now, NCAT is. And that's the ideal way to know if you're going to get good performance. I think I just told David that, most states allow between 10 and 20% wrap in a mix with polymer. Ideally, Arkansas should have, most states don't have, but it'd be in a perfect world, all the states would have a performance test where, hey, if a contractor puts 20% wrap and it passes, you approve it and you're good to go. So a balanced mixed design approach, it may limit the wrap depending on the type of wrap material, but you may find that contractors can get different types of binders and things like that where they can go to a higher wrap content. So, but it's possible it may limit it a little bit.
Awesome. Thank you, Mr. Musselman. I appreciate you delivering this presentation. I know you have been sick. I hope and that you will fully recover.
I'm doing better now. Yeah. Thank you.
Yeah. Well, I'll keep you in my thoughts and prayers. So please let us give a round of applause for Mr. Musselman.
Thank you all.
All right. So now we are moving towards the last presentation of this technical session. And so the last one would be given by Mr. Martin Black Martin. Mr. Martin is a project manager and team leader on Gerber's construction services team with 18 years of experience. His responsibilities include providing construction management and engineering services on a wide variety of construction projects. He has provided construction management and engineering services for roadways, bridges, water, and sewer relocations. pump station installation and rehabilitation and treatment plant rehabilitation, as well as railroad and airport projects. Blake is currently serving as resident engineer for the RDOT 30 crossing project in downtown Little Rock and North Little Rock. Blake has a Bachelor of Science in Civil Engineering in 2003 and Master of Business Administration 2021 from the University of Arkansas. He's a registered professional engineer in Arkansas, Mississippi, Tennessee, and Georgia. Please help me welcome Mr. Blake Martin, and I'm going to pull up your presentation. So that would be. Can everyone see the presentation slide?
No.
That not yet. Okay, so I have to do new share. So that would be not I-30. Yeah, so this is how about now? Not yet. Okay, stop sharing. Good now. All right, let's make it full screen mode then.
There you go. I think you're right. Yep.
Good.
All right.
All right.
I'm glad you're doing that. 'Cause
Yes, Alice.
All right. Well, thank you for having me. Like I say, my name is Blake Martin. I'm from Garver. And I am the resident engineer for the 30 Crossing project. Just a little bit of history about the project. It's the first design build project that RDOT's undertaken. And the largest contract to date that RDOT's done, currently valued at $632 million. Just for, or 633, just like 632.8 or something. Anyway, just to kind of give you a little background on it. The phase 1 project that's under construction now in downtown Little Rock and North Little Rock is a 4.7 mile segment. Basically from the north terminal interchange where Interstate 30 and Interstate 40 come together in North Little Rock, down to the 630-30 interchange in downtown Little Rock. So it's replacing some infrastructure that is functionally and structurally deficient, including the river bridge that was a fracture critical.
It's just not advancing, so you're online, so he may be able to do that. Let me.
Okay.
So we right here. So we stop the screen sharing for a second. And then where's yours? There's yours. Okay.
Online folks, so we realized that the slides are not advancing, so he is getting it fixed now.
Right there. Yep. So that's the one, right?
Yep. Good to go. Okay. All right.
Are you able to see the advancing?
Yeah, I think
Okay.
he
Yeah,
think
he
he saw
did
it there.
it.
So,
Yeah. Thank you.
like I said, that the job replaces the major river crossing there of Interstate 30 over the Arkansas River, which was a fracture critical structurally deficient bridge built back in the 1960s. So, like I say, this is the first design build project that RDOT's undertaken, and with the complexity of this corridor, that brings you the collaborative effort of engineering and construction to the table at the same time. So a little further into back into history, 30 Crossing was one of the 31 projects that the voters of Arkansas voted in with a 1/2-cent sales tax in 2012. Shortly thereafter, we began the Pell study and the NEPA study. All the way, it brings us up to over the next couple of years. And in 2017, went out with RFQ for design build firms. Shortlisted 2 of them, Kiewit Massman, which was the one that selected, and Granite was the other one that was shortlisted. Went through the interview process. So in 2019, RDOT got FHWA's FONSI, which let the project move towards construction, and we issued the notice to proceed number 1, which was for design only in early 2020.
And then notice to proceed 2, which allowed them to begin construction, was issued about mid 2020. And construction in earnest started in September of that year. So we're just a little over the 2 years into construction at this point. So some of the phase 1 milestones that have happened in 2022 and will happen in early 2023 are up here on the screen. We made the final deck pours on the eastbound river bridge back in July and moved traffic over there in September. Then in this final quarter of 2022, close the final westbound ramp with that traffic switch that got you to 2nd Street, or the Cantrell interchange as some people call it, and also the 6th Street ramp, and reopen the 9th Street ramp that was closed early in the project as the only ramp into downtown off Interstate 30. The next milestone on the Little Rock side is to set the girders on the 6th Street bridge, and that's scheduled for the weekend of Veterans Day, so about 10 days from now. We'll do a complete shutdown of Interstate 30 to do that, and on Friday night, and by the hour schedule we've got right now, we'll be open back up by Sunday morning, which is for westbound, that's going to create a little bit of a long detour route because there's no way around it like we've done in the past with 9th Street. But eastbound traffic will still be able to exit on the frontage road, go around and get back on its new ramp. As far as milestones in North Rock, closed Interstate 40 over a weekend back in August. Set those girders across Interstate 40. That's what we all refer to on the project as the weave bridge that will fix the weave that is eastbound up there in North Rock. The deck pour for that bridge is set for this week. As you see, that one's highlighted in the next box down. That deck pour will be this week. And then we've got the temporary on-ramp at Bishop Lindsay and Broadway. The Broadway entrance ramp closed, so you're using a temporary ramp there in North Rock. So over the next 10 days, those final 3 milestones for September through December 2022 will happen. And then the biggest milestone kind of in the River Bridge area will be pouring the deck on 6th Street sometime in early February. And they've got a intermediate milestone to have 6th Street Bridge back open. I believe the date's in early April. So here's a picture for the 630 interchange from late 2021. I was trying to see if the mouse worked on the screen. No. So early in the project, we rebuilt the 6th and 9th Street ramp off of eastbound. That's the one that's in concrete, kind of on the right side of the screen. And we already completed the ramp from the 630 East to 30 East ramp. That would be the ramp onto the northbound frontage road. That'll be the new ramp, or is now the only way to get from 630 directly into downtown when the Cantrell interchange closed. So here's a traffic switch that we just undertook a couple weeks ago of doing some shifting on that 30 West to 630 West ramp. Shifted them to the right a little bit. This is a portion of the project that was added by my change order, added scope to the project. So we're now rebuilding this ramp from 30 West to 630 West. And like I say, you've seen a traffic switch, so that work is now underway. Here's another shot from that interchange. You see the new 2-lane exit ramp from 30 eastbound to 6th and 9th Street there with concrete pavement. We also rebuilt the on-ramp to westbound over there by the law school on the left side of the picture to a 2-lane on-ramp as part of the project. And then the bridge over that on-ramp I'm talking about is newly added scope that we just had a traffic switch on because we're going to replace that bridge over that ramp now. And you can see 9th Street Bridge kind of in the background of the picture up there in new concrete that's open, and the 6th Street Bridge has been demolished at that point. So here's kind of the comparison of 9th Street from before the project to rebuilt, almost 2 years apart. So 9th Street Bridge got wider and longer. It's now got 14-foot walking paths down both sides as a request from the city of Little Rock. And they funded that portion of the bridge. Here's kind of another aerial shot of the bridge completed there in the bigger picture and during construction almost a year ago. Here's the 6th Street Bridge. After it's removed, there's a picture down in the lower right of that closure back in the spring and April to do the demo. And that was another weekend closure of close both directions and do it in a weekend rather than try to do it over nightly closures over 2 or 3 weeks. Here's the Cantrell interchange at the beginning of the project, 2nd Street interchange. Some people call it, with the 3 loop ramps and the viaduct going into downtown. And as I mentioned earlier, that last loop ramp there on the left is now out of service. It's not completely demolished yet because that's the contractor's exit from the bridge demo at the moment. But all the rest of them are gone. The Cantrell viaduct's gone. Here's an updated photo to kind of show you that. You see part of the old river bridge is gone. That one loop ramp still in. All the loop ramps on the President Clinton side there on the east side or the right side of the photo are gone. Even the viaduct going into downtown's gone, and 2nd Street's been widened already. Here, a couple more photos of the demo of those ramps. This is on the west side of Interstate 30, looking back towards the east. You see some of the viaducts gone in the bigger, larger photo on the right, and the contractor's using some of that area as lay down space at the moment. So more pictures of the Cantrell viaduct. The one on the left being during the demo, the one bridge over Cumberland. There remains, and that's the trolley power supply in the green box underneath the bridge. So it took a little extra time to do that demo. And then the picture on the right there with the green space, you can see the same transformer there in the lower of the screen to kind of give you an idea of before and after. And that's final configuration down there in the lower right. It's basically going to be green space that the city of Little Rock is working with RDOT on to come up with a plan of what to do. Here's a rendering of the final configuration of the project. You're on the Little Rock side looking to the north. You see all the green space that the project's opening up from all the loop ramp demo. This is another rendering shot. Looking west to east, you see the Clinton Library there in the background of the picture, and how the loop ramps for the Cantrell viaduct being gone will open up lots of green space in downtown. So as I mentioned, we hit the major milestone about 6 weeks ago of getting traffic off the old structure and onto the new structure. That was a 3-phased approach of first moving just the ramp traffic. That's the picture in the upper right-hand part of the screen. We had a temporary on-ramp onto I-30 that was over eventually where 30 main lanes were going to be. So move the ramp, demo the ramp, do some paving in a 10-day window. And then step number 2 in the lower left there is put main lane eastbound 30 in its configuration for the traffic switch. And then stage number 3, you see we had to do some paving for a crossover to get westbound on back over to westbound's original pavement. So lots of work happened in that 3-week period of demo and paving to get that major milestone. So that's 2 years since the day we began, nearly, to get us from existing bridge to traffic on the new eastbound structure. So now we're in demo of the current bridge and about to start back in on construction of the new westbound structure. Here's an aerial shot looking. The one on the left-hand side of the screen is looking to the north. You see what we were just talking about, the traffic switch and the crossover down there on the bottom, the new river structure, and the old river structure that is now out of service there on the left-hand side. And then the picture on the upper right is a picture of the south, of what we call the south approach that was under construction from September 2021. You see caps and column work going up there with traffic on the old structure. So kind of gives you a perspective of how much was accomplished in a year there. Couple more shots south looking north, kind of both the same the direction. You can see the loop ramp in both pictures, kind of give you a perspective of where you're at. So a couple, while we're looking at this shot, the upper right hand picture, a couple interesting things that I think are first in RDOT history that I know of, and somebody may correct me. The current eastbound bridge that's trafficking on has 2 post-tension concrete caps on it. That's the first time that's happened in Arkansas, as far as I know, anywhere. We also, this being a design build project, there were a few other things that were done slightly differently than RDOT's normal standard specification. Is those 2 post-tension caps have 6,000 PSI concrete in them and 35% fly ash, which is way above RDOT's typical Class S and 20% rule. All the drilled shafts on the project, and that's 15 of the 16 vents on the river bridge, are all 5,000 PSI concrete, which is above normal Class S concrete that's used for substructure work on an RDOT bridge. Here's the new river bridge open to traffic with demo started just over a month ago. At this point in the last month, all the deck is off the bridge, the old bridge. Even some of the floor beams and stringers are coming off later this week, if not the first of next week, kind of depending on reassembly of the big river crane. They will start the first pick of the 2 main girders, of removing the 2 main girders of the old bridge. Kind of another comparison shot of demo, from a month ago and October of last year, when we were just setting structural steel on the bridge that traffic's on now. So there's the Interstate 30 River Bridge there on the left-hand side of the screen. Like I say, September 2020 when we started. And there it is a year later, 2 years later, excuse me, with traffic on it and demo started. So in the course of 2 years, built that new structure across there. Here's some north approach pictures. This is the North Little Rock side of the river. You're basically kind of at the river. You can see it in the bottom of the picture on the left, with traffic on the new structure and demo already underway. You see the big cellular abutment there on the left side that was used for storage by RDOT maintenance for a long time in demo. And then north approach back in December, right before the first deck pour in that section. Here's the Broadway exit into downtown North Little Rock. You see how it was in December 2021, basically earthwork going on. Basically 9-10 months later, we've got completed bridges over Broadway and Washington, 2 there at Washington and 1 at Broadway, and the new ramp open at Broadway into downtown North Little Rock. So here it is, September 2020 on the left when the project started, and 2 years later with those bridges completed and the new exit. As far as north of Broadway, you see the temporary off ramp that we used into downtown North Little Rock while we're rebuilding that there on the right. The new temporary on ramp that is now in use for Broadway there on the left. Since the one down there in front of Simmons Arena is out of service since the river bridge is gone. So up in the north terminal, this is the bigger shot there on the left. That's what we call the weave bridge. That's the one I talked about. We closed Interstate 40 down through the north interchange back in August and set those girders. That yellow crane that you see in the picture had to had to sit right out in the middle of Interstate 40 to make that pick. There was no way to do that in nightly closures. That's a simple span bridge, and it had 2 splices in the girder, so you had to put them together on the ground. Where the temporary tower would have been in the lanes if we'd have done it piece by piece. So the only way to do it, bigger crane and set the structural steel all in one lift. Picture in the upper right is from a year before. Now that bridge right there will fix what everybody refers to the weave in the north interchange, how Interstate 30 comes in on the right and Interstate 40 comes in on the left of that 4-lane section there eastbound. With this bridge, Interstate 30 will now come in the left with 67 and 167 leaving on the left on the other end, and Interstate 40 will be a through movement through the 8-lane section in front of what everybody refers to as the big church in North Little Rock. So 30crossing.com is a great resource for knowing where all the mini closures are for city streets and main lane closures overnight, or the weekend closures and detour routes that are coming up. So if you go through the corridor, make yourself familiar with this, because it's an ever-changing place. I promise you that. There's the website. There's a email address that is monitored by some of the communication staff at Garver who reach out to me if they need to, and also a phone number directly to them as well. So. Anybody got any questions?
Wait,
Yes, sir.
what's going to happen with the railroad yard overpasses? I know early on, railroad was not playing ball whatsoever.
That's correct. Those bridges are not in the current scope of the project.
Okay, so that is still the current status.
Yes. There is a mill and overlay from the Broadway Bridge to the north that we will make it from 3 lanes to 4 lanes, but there is no work on in the project. It's still not going to be addressed right now. Yes. Yes.
In addition to those, we got to do something with city.
Yeah.
Okay, and in addition to the main lane bridges, you have to do something with the frontage road and the city bridges on either side too?
That's correct. Yes.
Okay.
Yeah, the railroad was very difficult to deal with during the preliminary design portion with what they would give the contractor with track time. So that was a big risk that both design builders put in their price. So to get the job in budget, that was something that was removed. So yeah, so the ultimate has a bridge built on the Cypress side where there's not currently a bridge now. You would replace the Locust Street Bridge that is there now. That's that 90-plus-year-old concrete slab span bridge, and then replace both mainline bridges to get you to the 5-lane each way configuration that is the ultimate design.
So we'll neck down, everything will neck down the current 3-lane configuration between Broadway.
You'll have 4 in North Little Rock. When you come across the river, you'll have 4 from basically the end of the river bridge till you get to the north interchange to have a 2+2 split at the north interchange. Whether instead of having the 3 to 2+2 split that you have now. That's eastbound anyway. Westbound's a different discussion. Huh?
Online folks, do you have any question for Black Martin? All right, thank you so much, Black.
Right.
Appreciate you.
Yes.
Yeah, we see like a couple of questions that I think that is for Zim. I do not know if he is still here. If he is here, then we can see if he can respond to that question. Yeah. Yeah, he kind of left. Okay, are there any kind of taker for we have a couple of questions? Like first, I don't know, balanced mix design. Does a balanced mix design approach limit the amount of prep without a specification limit? Yeah, it's for the previous one, previous presentation. If there is no taker for this question, I do not want to respond to that either. And the second one was for the coal type. Anyone from the speaker, from the attendees online, can anyone share or say anything about that question? It was, I believe it was a little bit too late since Jim already left. He answered those? Oh, okay, okay, great. All right. Folks, looks like there is no other questions, so we are about to adjourn. But before that, I would like to mention about a couple of things. The PDA's Professional Development Hours form. Again, please email me and then we will issue a certificate. And those folks here in the room, you can either give it to us now, or if you feel comfortable, you can send it to us later on via email. And I'd like to thank again for all the speakers, attendees, volunteers, staff members, and the support that we have received in organizing and executing this event. So have a great day. And now officially we are adjourning this summit. Thank you all. Bye-bye.